Everything you've ever loved, every star, every law of physics began as a question mark in the dark. Then, suddenly, the universe was here. The Big Bang explains how space expanded, how matter cooled, how light ignited, but it dodges the most dangerous detail. If time itself began there, what could possibly cause the Big Bang? And what does nothing even mean? At the farthest edge of the cosmic record, our equations stop behaving like stories and start acting like cliffs. We can measure the universe with exquisite precision. Yet the moment we reach its first boundary, explanation turns strangely fragile. Cosmology is often described as a tale of origins, but it is built like a courtroom case. Evidence first, imagination second. When we rewind the sky, the universe does not fade into darkness. It sharpens into patterns we can test. Galaxy light stretches as space itself expands, and that expansion leaves a mathematical rhythm across the largest structures. A faint microwave afterglow fills every direction, carrying tiny temperature ripples that map the universe's ingredients and shape. Even the first few minutes left chemical fingerprints, hydrogen and helium in precise proportions, with a stubborn mismatch that refuses to go away. And yet, as solid as this case becomes, it points toward a limit where earlier may not be a usable word. General relativity makes time part of the system, not a backdrop, and that detail changes what it means to ask for a cause. The closer we push toward the beginning, the less the question resembles a trigger we could film, and the more it resembles a boundary condition written into reality. To cross that boundary, physics offers bold proposals that keep their distance from fantasy. Some suggest a brief era of accelerated expansion that set the stage for everything we later observe. Others replace a singular start with a rebound, a cycle, or a quantum transition where classical space and time are not yet fully formed. Each option carries a price: new assumptions, new uncertainties, and new predictions that might be hunted in the sky. Then the word nothing enters the story, and it refuses to stay simple. In modern physics, empty space is not empty in the everyday sense. Fields persist, the vacuum has structure, and the lowest energy state can still have consequences. What looks like absence can behave like a medium with pressure, with instability, with hidden thresholds. If a beginning can be linked to anything at all, it may be linked to this strange kind of emptiness that is not quite empty. But the final challenge is not only physical, it is logical. Causality is usually a chain of earlier events pushing later ones, and that chain depends on time already being there. If time emerges with the universe, the demand for a prior push may be the wrong shape of question. The real task becomes sharper and harder. Define what counts as an explanation when the stage, the clock, and the rules are part of what must be explained. This film follows that edge with discipline, separating what is measured from what is merely tempting. We will treat the Big Bang not as a dramatic blast in a pre-existing void, but as a signpost where our current descriptions reach their limits. And we will ask how far careful inference can go before it must hand the story to deeper laws. Because the most unsettling possibility is not that we lack an answer, but that we have been using the wrong meaning of before, the wrong meaning of cause, and the wrong meaning of nothing. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with the evidence that earns cosmology its confidence, then descend through the earliest timeline to the first instance. From inflation to bounces to the physics of vacuum and time itself, we search for clues that might still be visible today. Before the first star, before the first atom, the universe was hotter and denser than imagination allows. Picture it not as a scene inside space, but as space itself. Compressed, energized, and changing everywhere at once. We call that story the Big Bang, but the name misleads. It sounds like an explosion, like a fireball thrown into empty space. The evidence points to something stranger, and in a way more unsettling. Space itself has been expanding, and the early universe was a state, not a place. The central question lands immediately, almost like a reflex. If the Big Bang created everything we can observe, what caused the Big Bang? The question feels simple because our language is built for everyday time, where clocks tick on regardless of what happens. Causes come before effects, and events happen inside a larger stage. But the Big Bang is not an event inside space and time in the usual sense. It is the earliest chapter our current physics can reliably describe, and even that reliability has edges. So we start by defining what the Big Bang theory actually claims. It says the universe was once in a hot, dense, rapidly expanding state, filled with radiation, particles, and fields in near thermal equilibrium. As space expanded, the universe cooled, and matter formed stable structures as temperatures dropped below key thresholds. Galaxies did not fly outward through pre-existing emptiness like shrapnel. The distances between galaxies grew because the metric of space changed, stretching the paths that light and matter follow. That difference matters because it changes what beginning can mean. If space is what expands, asking where the Big Bang happened can be like asking where on Earth the North Pole begins. Every direction points away, yet no location is privileged. The question assumes a background that may not exist. The same problem appears with the word before, because before assumes time is already there to be measured. If time is part of the system that began evolving from that hot state, before may stop being a physical coordinate. Still, this is not a retreat into poetry, because cosmology earns its claims with measurements. The Big Bang model is anchored to tests, and that is why it dominates modern cosmology. We can measure the present expansion of space through the Hubble. Lemaitre law, a relationship first glimpsed in the early 20th century. Distant galaxies show redshifts that scale with distance, consistent with a stretching of wavelengths as space expands. In images, those galaxies look serene and fixed, yet their light carries a subtle drift toward red, an imprint of the universe's growth. We can map that expansion across cosmic time using supernovae, galaxy surveys, and standard rulers. Type Ia supernovae act like calibrated beacons because their peak brightness follows patterns that let us infer distance. Baryon acoustic oscillations provide a statistical yardstick, a preferred scale frozen into the distribution of galaxies. Each technique has its own systematics, and each is cross-checked against the others. Together, they turn the sky into a kind of timeline, where distance becomes a proxy for looking back in time. We can also listen for the universe's earliest echo. The cosmic microwave background is relic radiation released when the universe cooled enough for electrons and nuclei to form neutral atoms. Before that moment, the cosmos was a hot plasma, and light scattered constantly, unable to travel far. After it, photons streamed freely, and they still fill space today, cooled by expansion into microwaves. The CMB's near-perfect blackbody spectrum is a triumph of precision, because it matches the signature of a thermal origin with extraordinary accuracy. Its tiny temperature variations, mere tens of microkelvin, are a fossil record of early conditions, like ripples preserved in ice. On a full sky map, those variations look like mottled color on a sphere, but they encode deep physics. They reflect sound waves in the early plasma, where gravity pulled matter inward and radiation pressure pushed outward. The peaks in the CMB power spectrum reveal the universe's composition, including ordinary matter, dark matter, and dark energy. They also reveal geometry, because the apparent size of those primordial ripples depends on how space is curved. In other words, the CMB is not just a picture of the past. It is a measurement of the universe's ingredients and its shape. A third test is chemical, and it reaches even further back. Big Bang nucleosynthesis predicts the primordial abundances of light elements, mainly hydrogen and helium, with traces of deuterium and lithium. Those ratios depend on the density of baryons and the expansion rate in the first minutes, when the universe was hot enough for nuclear reactions. As the cosmos cooled past a few billion degrees, protons and neutrons began assembling into helium nuclei. But the timing mattered, because free neutrons decay, and the expansion rate set the window for building heavier nuclei. Observations across old gas clouds and ancient stars broadly match the predictions, especially for deuterium and helium. Deuterium is particularly sensitive because it is easily destroyed in stars. So finding it in pristine gas tells us about the early universe. Lithium is more complicated, and its mismatch hints at astrophysical processes we may not fully model. Even so, the overall pattern is striking. Together, expansion, relic radiation, and element abundances form a tight triangulation, where independent lines of evidence converge on the same early hot phase. These successes tell us what the Big Bang is, and they also tell us what it is not. It is a framework describing how the universe evolved from an early, hot, dense phase into the structured cosmos we see. It does not automatically tell us why that phase existed. It does not automatically tell us whether there was a first moment. It does not automatically tell us what nothing means, or whether that word belongs in physics at all. The word nothing carries at least two meanings, and they collide in this debate. Philosophical nothingness is the absence of anything at all. No objects, no space, no time, no laws. It is not a vacuum, because a vacuum is still a kind of something. It is not emptiness inside a container, because the container would be something. In that strict sense, nothingness is hard even to define without smuggling in structure, like a hidden stage behind the claim. Physics uses a different nothing in many contexts, and it is more technical than the word suggests. The quantum vacuum is the lowest energy state of fields that exist everywhere, even when no particles are present. Even in perfect emptiness, quantum fields have fluctuations and correlations, constrained by uncertainty relations and by the field's symmetries. Virtual excitations appear in calculations, and vacuum energy can have measurable effects, as in the Casimir force between close metal plates. The vacuum can be structured with phases, symmetry breaking, and possible metastable states, quiet but not featureless. This is where confusion becomes fuel for bad explanations. People hear that particles can pop out of the vacuum, so they imagine the universe popping out of nothing. But the quantum vacuum is not philosophical nothingness, and it never claimed to be. It presumes fields, rules, and a notion of time in which fluctuations occur, even if that time is subtle. If the question is why there is a universe rather than nothing at all, the quantum vacuum may not be the right starting point. Yet it remains relevant because our best cosmological models are built out of fields. The vacuum might still matter for cosmology in a more precise way. In modern theories, what we call empty space can carry energy that affects expansion, and that energy behaves like a negative pressure in Einstein's equations. Vacuum-like energy can drive accelerated expansion, and it may have played a role in the earliest moments. The vacuum can also undergo transitions, changing the effective laws and particles that emerge at low energies. So nothing in physics is slippery, and the documentary will keep returning to that slippage, because it changes what counts as an explanation. To ask what caused the Big Bang, we have to follow the evidence backward, step by step, toward hotter and denser conditions. As we rewind cosmic history, the universe becomes simpler in some ways, because distinct forces and particles begin to merge into unified descriptions. At early times, atoms can't exist, then nuclei cannot exist, then even protons and neutrons dissolve into a quark-gluon plasma. In laboratory accelerators, we briefly recreate hints of such plasmas, but the early universe sustained them everywhere. The physics becomes more unified, but also more extreme, and that combination is where confidence begins to thin. Eventually we reach energies where our tested theories are stretched beyond their domain. General relativity is the backbone of the Big Bang description, and it has passed every precision test we can throw at it on astrophysical scales. It links the geometry of space-time to the energy and pressure of matter and radiation, turning mass and energy into curvature. When applied to an expanding universe filled with ordinary matter and radiation, the equations imply that the past includes a singularity. Densities and curvatures blow up as we extrapolate to a time when the scale factor goes to zero. That singularity is often treated as the beginning of everything, a dramatic punctuation mark at the start of time. But in physics, a singularity usually signals that a theory is being pushed past where it works. Infinite values are not usually literal features of nature, because nature tends to regularize extremes through new effects. They are warnings that important physics is missing, often quantum effects that classical equations cannot capture. The Big Bang singularity may be a boundary of our current model, not a point we can confidently describe. It is less a destination than a sign that says, beyond this, the map changes. There is also a historical lesson hidden here. When Newtonian gravity predicted infinities at the center of certain idealized systems, it was not the universe confessing to literal infinities. It was a clue that a deeper framework was needed, and general relativity provided it. In the same spirit, a cosmological singularity may be telling us that space-time itself must be treated quantum mechanically. That does not guarantee a bounce or a prior phase. It only tells us that the classical story ends before the questions do. This is the edge of the story, where the camera lingers on what we can measure and what we can only infer. We have a well-tested account of the universe, back to a fraction of a second after the hot phase began, and in some respects, even earlier through statistical traces. We have precise measurements that lock down many parameters, from the baryon density to the age of the universe. But when we ask about the first instance, we run into horizons of knowledge. Some horizons are literal, like the limit set by the finite speed of light. Others are conceptual, like the limit of applying classical spacetime to quantum regimes. Horizons will be a recurring motif because they define what can leave a message. The CMB is a message from a time when the universe first became transparent, a surface of last scattering that wraps around us in every direction. Element abundances are messages from the first minutes, written into the chemistry of ancient gas. Large-scale structure is a message from tiny early fluctuations grown by gravity, amplified over billions of years into filaments and voids. The universe keeps records, but it does not keep every record. Earlier than certain epochs, information may be scrambled, erased, or locked behind limits we cannot cross. Echoes are another motif because cosmology often works like archaeology. With inference as its primary tool, we infer the unseen from patterns left behind, and we test those inferences by seeing whether different records agree. Tiny anisotropies in the CMB encode the seeds of galaxies, and their statistical properties can distinguish between competing early universe scenarios. The distribution of matter encodes the same primordial perturbations, but processed by gravity and cosmic expansion. Even gravitational waves, if detected from the early universe, would be a new kind of echo, one that travels through matter almost untouched. Each echo narrows the space of possible beginnings, not by telling a story, but by ruling out stories that cannot fit the data. But the closer we approach the putative beginning, the more the idea of cause becomes unstable. In ordinary experience, causes precede effects in a shared time, and the background clock is never in question. If time itself is part of what is emerging, then causal language may need revision, or at least careful translation. Some models replace a beginning with a transition, like a bounce from a prior contracting phase. Some models treat the Big Bang as a boundary condition rather than an event, a starting rule rather than a starting explosion. Some models suggest time may be emergent from deeper, timeless laws, so that earlier is not fundamental but approximate. At this point, a thought experiment can sharpen the tension. If you remove time as a background parameter, what does it even mean to say something happened, or that one thing triggered another? Our brains insist on narrative, because narrative is how we survive in a world of sequences. Yet the universe may not share our intuitions at its deepest levels. The question is not whether causality is real in everyday life. The question is whether it remains the right tool at the edge where our equations falter. This documentary will not pretend that one answer is already known. It will treat the question as an investigation with constraints, where the most important discipline is to separate evidence from extrapolation. We will separate what is measured from what is inferred, and we will mark the difference out loud. We will track where equations are tested and where they are extended beyond the lab and the telescope. We will be explicit about assumptions, because cosmology is often a debate about which assumptions are justified and which ones are simply inherited from common sense. Here is the map for the series. First, we establish the evidence for the Big Bang and what it does and does not claim. Second, we push toward the earliest times we can model with confidence, and we mark where uncertainty begins. Third, we examine inflation and quantum origins, including what inflation explains and what it leaves open. Fourth, we explore alternatives like bounce and cyclic scenarios and what signatures they might leave. Fifth, we consider multiverse ideas and vacuum decay and how they change the meaning of explanation. Sixth, we confront the nature of time and causality and whether before is ever physical. Seventh, we ask what remains meaningful to ask when language outruns testable physics. Each step will keep returning to the same tension, because it is the engine of the mystery. The Big Bang is strongly supported as an early, hot, dense phase, and the evidence for that phase is not fragile. The cause of that phase is not settled, and may not even be a well-posed question in the way we instinctively frame it. Nothing might mean empty space or a quantum vacuum or the absence of laws, and those are not interchangeable. The singularity might be a real boundary, or it might be a signpost that points beyond general relativity toward a quantum description of space-time. We end this opening chapter with a disciplined reset, because clarity is part of the drama. The mystery is not whether the universe expanded from a hot beginning, because the sky itself keeps repeating that message. The mystery is what that beginning really was, and whether beginnings require causes, or whether cause is a concept with a limited domain. If we're going to ask what caused the Big Bang, we first need to know what the Big Bang is and how we know it happened. We begin where cosmology earns the right to speculate, and we begin with measurements that do not care what we want the origin to be. The universe does not negotiate with our intuitions. It leaves traces, and those traces either line up or they do not. In this chapter, we follow the traces that survive the longest and speak the clearest. The Big Bang model is not a single clue, and it is not a slogan that explains everything at once. It is a convergence of independent records, gathered with different instruments and different assumptions, that still point to the same early hot phase. Each record is imperfect on its own, yet their overlap is what makes the case persuasive. First is expansion, the simplest observation with the most profound implications. In the 1920s, Edwin Hubble and others compared galaxy distances with their spectral redshifts, using the newly developed language of extragalactic astronomy. The farther the galaxy, the more its light is shifted toward red, consistent with space stretching during travel rather than light losing energy by friction. On screen, the idea is almost too clean. A galaxy's spectrum, with its dark absorption lines, slides steadily to longer wavelengths. Those lines are chemical fingerprints, and they move together as a rigid pattern, an unmistakable sign that the shift is not a local distortion. When we translate that shift into a recessional velocity, the numbers climb with distance like a rising tide. That relation is not just historical, and it is not frozen in the era of photographic plates and hand-drawn plots. Modern surveys map redshift across millions of galaxies, and the pattern still follows an expanding universe with a definable rate. The data now arrive as dense point clouds, and yet the same underlying trend remains visible through the statistical haze. In the background sits a subtle distinction that matters for origins. Galaxies are not simply flying through static space like shrapnel from an explosion. Space itself is expanding, and that expansion changes the meaning of distance. The redshift is, in that sense, a record of the universe's scale factor, a cosmic ruler that has been stretching for billions of years. Distance is the hard part, because we cannot walk a tape measure to another galaxy. Astronomers build a ladder of methods that overlap and cross-check, because no single ruler reaches across the whole cosmos. Each rung is calibrated against the one below, and the entire structure is tested by consistency, not by trust. Nearby, parallax anchors distances geometrically, using Earth's orbit as a baseline. A star appears to shift against the distant background as we move from one side of the Sun to the other, and that tiny angle can be turned into a distance by simple trigonometry. Modern space missions measure parallax with astonishing precision, shrinking uncertainties that once dominated the ladder. Farther out, Cepheid variable stars provide a calibrated brightness relation that turns flux into distance. Their pulsations are not random flickers. They arise from a physical instability in the star's outer layers, where ionized helium alternately traps and releases heat. The period of the pulse correlates with intrinsic luminosity, so time itself becomes a measuring stick. In visuals, Cepheids are almost cinematic, a star swelling and dimming in a steady rhythm, like a heartbeat seen from across the galaxy. You watch the light curve rise and fall, and from its tempo, you infer what the star truly is. Then you compare that true brightness to what you observe, and distance emerges from the difference. Beyond that, Type Ia supernovae act as standard candles, bright enough to be seen across a large fraction of the observable universe. They originate when a white dwarf in a binary system undergoes runaway thermonuclear burning, producing a remarkably uniform explosion. Their peak brightness is not identical, but it is correctable through light curve shape and color, which track how the explosion unfolds and how dust reddens the light. When those supernova distances are plotted against redshift, the curve reveals more than expansion, and it reveals more than a single number. It reveals that expansion has changed over time, which means the universe has a dynamical history rather than a simple linear drift. The plot becomes a kind of biography, with the slope and curvature telling us how the cosmos aged. In the late 1990s, supernova teams found distant explosions dimmer than expected in a decelerating universe, even after careful corrections. The simplest reading was acceleration, driven by something like vacuum energy, a smooth component that does not dilute the way matter does. The result was not embraced because it was elegant. It was embraced because the data kept pointing in the same direction. Expansion is also measured without supernova, and this matters because independent methods are harder to fool. Standard rulers use known physical scales imprinted in matter, then read their apparent size across redshift. If the ruler's true length is known, its apparent size becomes a distance indicator, and distances become a test of cosmological models. Baryon acoustic oscillations provide that ruler, and they are a preferred separation scale in galaxy clustering, set by sound waves in the early plasma. In the first hundreds of thousands of years, photons and baryons were tightly coupled, behaving like a fluid with pressure and inertia. A small overdensity would try to collapse under gravity, but radiation pressure would push back, launching a spherical wave. With BAO, galaxy surveys become a cosmic tape measure, and the tape is written into the distribution of matter itself. They constrain how distances grow with redshift, and they check the supernova story with an entirely different systematic budget. On screen, the universe looks like a web, filaments and nodes, and hidden within that web is a faint, statistical ripple at a characteristic scale. A third route uses the cosmic microwave background itself, and it links early physics to late-time distances in a single calculation. Its angular features depend on geometry and expansion history, because the same physical scale can subtend different angles, depending on how space has stretched. The CMB therefore acts like a backlight, illuminating the shape and contents of the universe all at once. These methods do not always agree perfectly, and the disagreement is not a footnote. The Hubble constant inferred from nearby supernova differs from the value inferred from the early universe, and the tension remains unresolved. It could be a sign of subtle measurement systematics, or it could be a hint that the model is missing a small piece of physics. That tension matters for the central question, because origins are sensitive to details. It reminds us that even strong evidence can hide missing physics, especially near the beginning, where energies and densities were extreme. If a parameter as basic as today's expansion rate is still debated, then humility is part of the method. Still, expansion alone does not prove a hot origin. An expanding universe could be cold and empty, unless we find a relic that demands heat. That relic is the cosmic microwave background, and it is the oldest light we can see directly. It covers the sky with near-uniform intensity, arriving from every direction as if the universe itself were a faintly glowing shell. If you could see microwaves with your eyes, the night sky would never be dark. In 1965, Arno Penzias and Robert Wilson detected a persistent microwave hiss while working with a horn antenna designed for satellite communication. It was not a local artifact, and it did not depend on season or direction, which is exactly what you would expect from a cosmic signal. They tried cleaning the equipment, chasing noise sources, even removing nesting pigeons. Yet the hiss remained. The historical context matters because the CMB was not discovered in a vacuum of ideas. Theoretical work had already suggested that a hot early universe would leave behind cooled radiation, and groups were actively searching for it. The discovery was therefore both accidental and inevitable. An instrument heard what the theory said should be there. The CMB is not just radiation, and it is not merely old light in a poetic sense. It is thermal radiation, with a spectrum astonishingly close to a perfect blackbody, the curve produced by matter and radiation in equilibrium. That blackbody shape is the crucial point, because it is hard to manufacture by any process other than genuine thermalization. The measured temperature today is about 2.725 Kelvin, only a few degrees above absolute zero. That number is not decorative, and it is not chosen to fit a story. It is the cooled remnant of a much hotter past, a temperature that has been diluted by cosmic expansion for nearly 14 billion years. A cooling, expanding universe predicts this in a straightforward way. If matter and radiation were once in thermal equilibrium, expansion stretches photon wavelengths and lowers their temperature uniformly, preserving the blackbody shape even as the peak slides to longer wavelengths. The spectrum is like a fossil that keeps its form while its scale changes. The CMB also explains why the early universe was opaque, which can feel counterintuitive at first. Before atoms formed, free electrons scattered photons constantly through Thomson's scattering, trapping light in a dense plasma. The universe was filled with radiation, yet it was as visually impenetrable as the interior of a star. As the universe expanded, it cooled, and cooling changes chemistry. Around 380,000 years after the hot phase began, electrons combined with nuclei and neutral atoms formed, mostly hydrogen and helium. With far fewer free electrons to scatter photons, the fog lifted, and light could finally travel long distances without being repeatedly deflected. That moment is called recombination, though it was the first combination, and the name is a historical artifact. The key effect is that photons decoupled and began free streaming through space, carrying with them a record of the conditions at that time. The CMB we see today is those same photons, stretched into microwaves by the expansion of space. So the CMB is a crime scene photograph, and the metaphor is more than stylistic. It is a snapshot of the universe when it first became transparent, preserved by the emptiness that followed. The image is not stored on film. It is stored in the sky itself, arriving at our detectors with the same statistical structure it had at last, scattering. But the photograph is not perfectly smooth, and that imperfection is where the story becomes intricate. The CMB has tiny temperature anisotropies, at the level of about 1 part in 100,000. On a full sky map, they appear as mottled patches of slightly warmer and cooler radiation, like faint weather patterns on a celestial globe. Those fluctuations are the seeds of structure, and without them, gravity would have nothing to amplify. A perfectly uniform universe would remain uniform, because there would be no preferred place for matter to gather. The galaxies, clusters, and filaments we see today are the grown-up versions of those early irregularities. The anisotropies are not random noise, and their pattern is not arbitrary decoration. Their statistical structure carries a precise signature of early universe physics, including the relative amounts of matter, radiation, and dark components. In cosmology, the power is often in the statistics, because the universe gives us only one sky to measure. In the primordial plasma, gravity pulled matter inward, while radiation pressure pushed outward, and the competition produced oscillations. The result was acoustic waves, sound in a cosmic fluid, propagating through a medium where photons supplied pressure and baryons supplied inertia. It is a strange thought. The early universe was loud in physics, even though there was no air to carry ordinary sound. When photons decoupled, those oscillations froze into the CMB as a pattern of hot and cold spots. Regions caught in compression appeared slightly hotter, while regions caught in rarefaction appeared slightly cooler, and Doppler shifts from moving plasma added further modulation. The angular power spectrum turns that pattern into a set of peaks, translating a sky map into a quantitative fingerprint. Those acoustic peaks are a soundtrack translated into numbers, and the translation is precise. Their positions and heights reveal the universe's composition and geometry, because each parameter nudges the oscillations in a distinct way. The first peak is especially important, because it anchors the apparent angular size of the sound horizon at recombination. The first peak tells us about spatial curvature, which is a geometric property rather than a local force. Its angular scale indicates the universe is very close to flat, within tight observational limits, meaning Euclidean geometry works well on the largest scales we can probe. That near flatness is not guaranteed by everyday reasoning, and it becomes one of the clues that the early universe had an unusual history. The relative heights of peaks tell us about baryons, the ordinary matter made of protons and neutrons. More baryons change the inertia of the plasma, enhancing compressions relative to rarefactions and shifting the balance between odd and even peaks. In plain terms, the amount of normal matter changes how strongly the early universe could ring. The peaks also demand dark matter, because ordinary matter alone cannot produce the observed pattern, while also matching the later growth of structure. Dark matter behaves differently in the early plasma, and that difference is exactly what the data require. It does not couple to photons, so it can begin clumping earlier and deepen gravitational wells without being held back by radiation pressure. Visually, you can imagine two overlapping worlds. One world, the photon-baryon fluid, is oscillating and resisting collapse, while the other world, the dark matter, is quietly gathering into potential wells. When recombination happens, baryons fall into those wells, and the universe's structure formation accelerates. The CMB also carries polarization, which adds a second layer to the photograph. Scattering off electrons imprints a preferred orientation in the light, and that orientation encodes velocity and density information that temperature alone cannot fully capture. Polarization is faint, and extracting it requires exquisite control of instrumental effects. Polarization splits into E modes and B modes, a mathematical decomposition tied to patterns on the sky. E modes are detected with high precision and match the same acoustic physics seen in temperature, providing a powerful consistency check. The E mode map looks like a delicate weave, aligned with the underlying density field at last scattering. B modes are more elusive, and their scarcity is part of what makes them valuable. Some B modes arise from gravitational lensing by later structure, which distorts E modes into a curl-like pattern, and those have been measured. Lensing B modes are themselves a map of the mass distribution integrated along the line of sight. Primordial B modes would be different, because they could indicate gravitational waves from the earliest moments. Such waves would gently shear space-time, imprinting a distinctive polarization pattern that cannot be produced by simple density perturbations. Detecting that signal would be like hearing an echo from an epoch far earlier than recombination. That window is not yet fully open, and the difficulty is not merely technical. Foreground dust in our own galaxy emits polarized microwaves, and instrument systematics can mimic signals if not controlled with ruthless care. The search therefore becomes an exercise in patience, calibration, and skepticism, because a premature claim would mislead the entire field. So the CMB gives us a detailed map of conditions at 380,000 years. And it gives us a model testing arena of extraordinary precision. It does not show us the first instant, but it shows us a universe already evolving under well-understood physical laws. The photograph is sharp enough to constrain subtle parameters, yet it still leaves the earliest chapter unread. To go earlier than the CMB, we use a different record, because light cannot help us before the universe becomes transparent. We use chemistry because the early universe briefly functioned like a nuclear reactor, and nuclear reactions leave behind measurable ratios. These ratios are not artistic impressions. They are numerical predictions that can be checked against the sky. Big Bang nucleosynthesis occurred in the first few minutes, when temperatures were high enough for nuclear reactions to proceed. The universe was expanding and cooling rapidly, and that rapid cooling is the reason heavy elements could not form in significant quantities. In a lab, you can hold temperature and density steady, But the early universe refused to wait. The theory predicts primordial abundances of light nuclei, and the list is short for a reason. Hydrogen dominates, helium-4 is substantial, and there are trace amounts of deuterium, helium-3, and lithium. Everything heavier is essentially absent, because the necessary reaction pathways are bottlenecked and the time window is brief. A key piece of the story is the neutron-to-proton ratio, which is set by weak interactions in the early seconds. As the universe cools, those interactions freeze out, and neutrons begin to decay with a known half-life. When nuclear reactions finally assemble helium, many surviving neutrons are locked into helium-4, because helium is the most stable light nucleus. The key control knob is baryon density, which determines how often nuclei collide and fuse. More baryons mean nuclear reactions proceed differently, changing deuterium and helium yields in calculable ways. Deuterium is especially sensitive, because it is both a stepping stone toward helium and a fragile nucleus that can be burned away. The expansion rate also matters because it sets the clock for the entire process. If the universe expands faster, neutrons have less time to decay before being locked into helium, raising helium-4 abundance. In that sense, helium becomes a probe of the early expansion history, and therefore of the energy content at that time. Observations test these predictions in multiple environments because we want the least processed material we can find. Deuterium is measured in pristine gas clouds seen in absorption against distant quasars, where the gas has undergone minimal stellar cycling. In spectra, deuterium reveals itself as a subtle offset from hydrogen lines, a tiny shift that demands high-resolution data. Deuterium is especially powerful because stars destroy it, and they do so efficiently. Finding it in unprocessed gas gives a direct handle on the primordial value, and the measurement becomes a stringent test of the theory. When the deuterium abundance matches the baryon density inferred from the CMB, two very different epochs agree on the same parameter. Helium-4 is measured in low metallicity regions where stellar processing is minimal, such as certain dwarf galaxies and H2 regions. Astronomers infer helium abundance from emission lines, correcting for temperature, density, and radiative transfer effects. The inferred abundance broadly matches nucleosynthesis expectations, which is remarkable given the complexity of the astrophysical environments. Lithium is the problem child, and its stubbornness is instructive rather than embarrassing. Observed lithium in old stars is lower than predicted, and the discrepancy may involve stellar physics, such as diffusion or depletion, or new early universe effects. The fact that one element misbehaves while others align forces us to ask whether the issue lies in the stars or in the early reaction network. Even with lithium tension, the overall agreement is striking, because the theory has very little freedom. Nucleosynthesis pins down conditions minutes after the hot phase began, long before recombination, and it does so with nuclear physics measured in laboratories. It is one of the rare places where cosmology and particle physics meet on equal footing. Now we have two early time anchors, and they are separated by an enormous span of time. The CMB fixes the universe at hundreds of thousands of years, and nucleosynthesis fixes it at minutes. Between them lies an epoch we cannot photograph directly, yet the numbers still connect across the gap. They agree on baryon density, and that agreement is not trivial. The number inferred from deuterium matches the number inferred from CMB peak structure. Despite completely different physics, different systematics, and different observational strategies. When independent methods converge, the space of plausible alternatives shrinks dramatically. That agreement is the point, because it is hard to fake with an ad hoc alternative. You would need to reproduce a blackbody spectrum, a specific anisotropy pattern, and a specific set of nuclear yields, all while keeping the expansion history consistent. The universe is not leaving us one clue, it is leaving a coordinated set. Next comes the late-time record, because the universe today is not a smooth plasma, but a structured cosmic web. It is structured into galaxies, clusters, filaments, and voids, and that structure grew from early fluctuations under gravity. The present-day sky is therefore a processed archive, shaped by nonlinear dynamics and astrophysical complexity. Large-scale structure is not just a picture of where matter ended up, and it is not merely a catalogue of galaxies. It is a transformed version of the same primordial pattern seen in the CMB, evolved forward through billions of years of gravitational collapse. The challenge is to decode that transformation without confusing it with local astrophysical effects. Galaxy surveys measure clustering statistically, because the pattern is subtle and the universe is noisy. They compute correlation functions and power spectra, looking for preferred scales and growth rates across cosmic time. The mathematics can feel abstract, but the idea is simple. Count how often galaxies appear separated by a given distance, and compare that to randomness. BAO appears again in this data, as a faint bump in the correlation function. The same sound horizon scale that sets CMB peaks also sets a bump in galaxy correlations at about 150 megaparsecs. It is a delicate feature, and detecting it requires enormous volumes of data and careful control of selection effects. This is a crucial echo, and it is one of the most visually satisfying consistencies in cosmology. The early plasma's sound waves left an imprint in light at recombination, and left an imprint in matter that later became galaxies. The two imprints match, and the match ties the early universe to the late universe with a single physical mechanism. On screen, the echo can be shown as two graphs that rhyme. One is the CMB power spectrum, with its sharp acoustic peaks, and the other is the galaxy correlation function with its subtle BAO bump. They look different, yet they are linked by the same physics. Pressure waves frozen into the fabric of matter and radiation. Structure growth also reveals dark matter, because ordinary matter interacts with radiation early on and cannot clump fast enough. Without an additional, non-radiating component, the universe would not have built the observed structures by today. Dark matter provides gravitational scaffolding, beginning to cluster earlier, then pulling baryons into its potential wells after recombination. We infer dark matter through multiple channels, and the list is long because the effect is ubiquitous. Rotation curves show stars orbiting too fast for visible mass. Gravitational lensing bends light more than luminous matter can account for, and cluster dynamics reveal extra mass in motions and temperatures. The CMB adds an early universe constraint, showing that the same component is required before galaxies even exist. None of these observations directly shows the particle, and that absence is part of the mystery. They show its gravitational effect, and they constrain how it must behave across cosmic time, such as being cold enough to clump on small scales. The evidence is therefore strong about what dark matter does, even if it remains silent about what dark matter is. Then there is dark energy, which enters as a late-time driver rather than an early-time seed. Supernovae suggest acceleration. BAO constrains distance redshift relations, and the CMB fixes a consistent global geometry that connects early and late epochs. Together, the best fit model includes a cosmological constant-like component, smooth and persistent, that changes the fate of the expansion. In equations, it is lambda, and in the model name it becomes LCDM, a shorthand that hides a great deal of work. LCDM is not a claim that we understand everything, and it is not a declaration of philosophical completeness. It is a compact accounting system that fits many datasets with a small set of parameters, and it earns its status by surviving repeated attempts to break it. In that accounting, about 5% is ordinary matter, the stuff of atoms and chemistry. Roughly a quarter is dark matter, and roughly 70% behaves like dark energy, driving accelerated expansion. These numbers are not derived from one plot. They emerge from the combined constraints of CMB peaks, large-scale structure, supernovae, and other measurements. This deepens the mystery of origins because the model that best describes the universe requires dominant components whose fundamental nature remains unknown. We can write them into the equations and measure their effects with precision, yet we cannot yet point to them in a laboratory with the same certainty. The universe, it seems, is willing to be measured without being fully explained. Yet the model's success is real, and it is not limited to broad strokes. It predicts the CMB spectrum, the acoustic peaks, the light element abundances, and the broad shape of structure growth. It also predicts subtle effects, including gravitational lensing of the CMB, the integrated Sachs, Wolf effect, and the way clustering changes with time as expansion accelerates. So why call the CMB a crime scene photograph, rather than simply a background glow? Because it is evidence that is both ancient and precise, and it constrains what could have happened before. The black-body spectrum restricts thermal history, the anisotropies restrict initial conditions, and the polarization restricts scattering and geometry. But every photograph has a frame, and every frame hides what lies outside it. The CMB is a surface of last scattering, not a view of the first moment, and it is limited by what photons can carry. Before recombination, photons were trapped, and before nucleosynthesis, chemistry had not yet written its ratios into matter. The closer we push toward the beginning, the fewer direct traces remain, and the more inference replaces imagery. Earlier epochs are inferred through delicate signatures, not directly observed scenes. We are reading the universe the way a geologist reads a cliff face, reconstructing events from layers that survived erosion. Anisotropies are one such signature, and their details matter. Their amplitude, scale dependence, and near-Gaussian statistics constrain the mechanism that produced primordial perturbations. The universe is not only telling us that fluctuations existed, it is telling us how they were distributed across scales, which is a clue to the physics that generated them. Polarization is another signature, and it adds depth to the record. It encodes scattering history and could encode primordial gravitational waves. But it must be separated from foreground contamination with careful multi-frequency observations. The work is painstaking because the signal is faint and the stakes are high. Large-scale structure is another signature, and it is both powerful and messy. It encodes the same initial conditions, but processed by non-linear gravity, feedback from stars, and galaxy bias, which is the imperfect way galaxies trace underlying matter. The challenge is to model those complications without erasing the primordial information we seek. Each record is partial, and no single dataset is allowed to dominate the narrative alone. The power comes from overlap, where the same parameters are measured by different physics at different times. When baryon density, curvature, and fluctuation amplitude agree across epochs, confidence grows for reasons that are mathematical rather than emotional. This is how cosmology builds confidence, and it is a discipline more than a mood. It does not rely on one heroic observation, but on a web of constraints that reinforce each other. When one thread is uncertain, the rest of the web can still hold, and the tension points to where new understanding may be needed. Yet we must be precise about what the evidence actually says, because precision is what separates science from myth. It supports an early, hot, dense, expanding phase that cooled into the universe we see. It supports a timeline with specific milestones, where minutes give nucleosynthesis, Hundreds of thousands of years give recombination, and billions of years give structure. It supports a set of ingredients that fit the data, and those ingredients appear as required terms in the equations. Baryons, radiation, neutrinos, dark matter, and dark energy are not decorative labels, but measured contributions to the cosmic energy budget. Each one leaves a distinct imprint, and the imprints can be cross-checked across time. What it does not say is equally important, because absence of evidence shapes the boundary of responsible claims. The evidence does not directly describe the initial cause, or even whether cause is the right category for the earliest moment. It does not show a literal explosion into empty space, and it does not privilege the imagery that popular language often supplies. Instead, it shows expansion of space, and it shows relics consistent with a hot beginning. It shows that the universe was once dense enough to thermalize radiation and young enough for nuclear reactions to set elemental ratios. It shows a cosmos with a measurable history, even if the first page is torn away. The evidence does not tell us what happened at time zero, if time zero is meaningful in physics. It does not tell us whether there was a before, or whether before is a category that breaks down when space-time itself is part of the system. The evidence also does not settle the meaning of nothing, because metaphysical definitions are not directly testable with telescopes. Still, the evidence changes what explanations are allowed, and it does so with quiet authority. Any origin story must reproduce the blackbody CMB, the anisotropies, and the light element abundances. Any alternative must also reproduce the BAO ruler and the growth of structure, matching the expansion history inferred from multiple distance measures. This is why the Big Bang model dominates, and the dominance is empirical rather than ideological. It is not because it is philosophically satisfying, and it is not because it answers every question we can ask. It is because it is empirically hard to escape, given the number of independent constraints that all point to the same early conditions. At the same time, LCDM leaves open deep questions, and those questions are not cosmetic. Why these parameters, and why these components, and why this near-flat geometry that seems balanced on a knife edge? The model fits, but the fit itself becomes a clue that we may be seeing an effective description rather than the final theory. It also leaves open the earliest mechanism that set the initial perturbations. The CMB tells us the perturbations exist, and it tells us their statistical character, but not their ultimate origin. We can measure the ripples with extraordinary precision, yet we still ask what first disturbed the surface. So we arrive at a disciplined tension, a stance that is both confident and incomplete. The universe gives us a clear record back to minutes, and a direct image back to 380,000 years. Beyond that, we are forced into inference, relying on statistical fossils and testing them by seeing whether independent fossils agree. The closer we get to the beginning, the more the investigation becomes about subtle patterns rather than dramatic images. The universe keeps records, but it does not keep them all, and it never labels them for our convenience. We are left to reconstruct, to compare, and to ask what kind of beginning could leave exactly these traces. And the central question returns with sharper edges, because evidence clarifies what is being asked. If the Big Bang marks the origin of our observable universe, what caused it, and what could nothing mean? The evidence takes us far back, but not all the way, and the boundary between what we see and what we infer becomes the stage for the next step. To approach the beginning, we need to compress time itself into an almost unimaginable timeline. In the next chapter, we will run that timeline backward, marking where known physics holds, where it strains, and where new ideas enter. We will keep the crime scene photograph in mind, because the oldest light is not the beginning, but it is the boundary where direct testimony starts. From that boundary, we ask what lies beyond, and we ask it in the only way the universe allows. Not as a story we prefer, but as a hypothesis that must survive the universe's remaining clues. We have a photograph of the universe at 380,000 years, and chemical clues from its first minutes. Now we do the controlled freefall backward, using those anchors to keep the story honest. We are not guessing in the dark. We are using measurements that survive the journey, even when everything else becomes unfamiliar. Start with what feels familiar, because familiarity is the last stable ground we get. Atoms exist, light travels freely, and the universe is transparent enough to leave a clean signal. In this late, calm era, the cosmos behaves like a readable medium. Photons can cross space without being constantly deflected. That transparency is not poetic language. It is a measurable optical depth, and it stays low once neutral atoms dominate. Picture intergalactic space as a deep, black ocean with a faint afterglow. Galaxies are islands of starlight, but between them, the darkness is not empty. It is thin gas, cold radiation, and expanding geometry. The void is threaded with magnetic fields, sparse ions, and relic photons that outnumber atoms by roughly 1 billion to 1. Even here, the past is encoded in the light that reaches us, because every photon carries a timestamp in its wavelength. As the universe expands, wavelengths stretch, and that stretching is not a side effect. It is the expansion written directly into the spectrum. A line emitted in ultraviolet can arrive as infrared, and the shift tells us how much space grew during the photon's flight. In a sense, redshift is the universe's bookkeeping system, quietly recording its scale factor in every arriving color. Rewind to recombination about 380,000 years after the hot beginning. Electrons bind to nuclei, mostly hydrogen and helium, and neutral atoms form across the cosmos. The word recombination is historical. There was no earlier combination, yet it captures the idea of charges pairing up into stable, electrically neutral matter. The key microscopic change is simple. Once electrons are bound, they stop acting like free scatterers for light. Before that binding, free electrons scatter photons constantly, and the universe is an opaque plasma. After binding, the scattering rate collapses, and photons decouple from matter. It is a change in mean free path. One moment light can travel only a short distance, and then it suddenly streams for billions of years. The same physics sits behind fog clearing on Earth, except here the fog is the entire cosmos. This transition is not instantaneous, and that nuance matters for what we observe. Recombination unfolds over a range of redshifts, producing a last scattering surface with a finite thickness in time. The CMB we measure is therefore a blurred snapshot, like a photograph taken through a slightly foggy lens. That thickness also sets a natural limit on how sharp the smallest features can appear in the CMB map. There is also a companion process that sounds similar but is distinct. Decoupling is about photons escaping, while recombination is about atoms forming. The two happen together because the same electrons control both, yet the language matters. When electrons bind, the plasma's electrical conductivity changes, and the photon-baryon fluid stops behaving like a single, tightly coupled substance. Those decoupled photons become the cosmic microwave background, stretched and cooled by expansion. The CMB is not the beginning, but it is the earliest light that can travel to us. Its spectrum is astonishingly close to a perfect blackbody, which tells us the early plasma was in near thermal equilibrium. That blackbody shape is so precise that deviations are constrained to parts in 100,000, an extraordinary statement about early universe uniformity. Today, that radiation is only 2.7 Kelvin, a whisper in the microwave band. Yet it fills all of space, arriving from every direction with almost the same intensity. When we map it, we see tiny temperature variations, tens of microkelvin, that act like a fingerprint of primordial density ripples. Those ripples are not merely pretty texture. They are the seeds that later become clusters, filaments, and the cosmic web. The CMB also carries polarization, a subtle directional pattern imprinted by scattering. Polarization is harder to see than temperature, but it is rich with information about velocities in the last scattering plasma. It is one more way the early universe left a structured record, like a second photograph taken with a different filter. The CMB marks a boundary in what we can directly see. Earlier than recombination, photons cannot carry a clear image, so we rely on indirect records. It is like trying to look into a furnace. Before the glass clears, you cannot see inside, but you can still infer what the fire is doing. The furnace analogy is literal in one sense. The early universe is a thermal cavity, and the CMB is its cooled, expanded glow. Even the small imperfections in the CMB are loaded with meaning. The pattern of hot and cold spots reflects acoustic oscillations, sound waves, in the early plasma, driven by gravity and resisted by radiation pressure. Those waves froze into place at decoupling, leaving a set of preferred angular scales that reveal the universe's geometry. The first peak is like a standard ruler, and its apparent size tells us whether space is flat, open, or closed. To picture those sound waves, imagine a drumhead made of light and matter, vibrating under its own gravity. Overdense regions try to collapse, photons push back, and the fluid oscillates. When the universe becomes transparent, the oscillation stops being driven, and the pattern is locked in. What we see as a hotspot is often a region where photons climbed out of a gravitational well, carrying a slightly altered energy. The physics behind that pattern is precise, and that precision is a gift. It lets us infer the baryon density, the dark matter density, and the overall curvature with remarkable accuracy. In other words, the CMB is not only an image, it is a calibrated instrument left behind by the early universe. The relative heights of the peaks even tell us how much ordinary matter was present, because baryons add inertia and change the oscillation balance. Historically, this idea matured through a chain of predictions and detections. The CMB itself was discovered in 1965 by Penzias and Wilson, first as an unexplained noise that would not go away. Later missions, COBE, WMAP, and Planck, turned that noise into a high-resolution sky map, and the map into a parameter set. With each step, the universe became less a mythic origin story and more an experimentally constrained timeline. Keep rewinding past the first stars and galaxies, past any chemistry made in stellar furnaces. We are now in an era where the universe itself sets the elemental baseline. Before stars ignite, there are no heavy elements to complicate the story, only the simplest nuclei forged in the first minutes. The periodic table, in this early view, is almost empty, just hydrogen and helium, with a few fragile trace species. In the first minutes, Big Bang nucleosynthesis turns free protons and neutrons into light nuclei. The outcome is mostly hydrogen, substantial helium-4, and traces of deuterium, helium-3, and lithium. This is the earliest chemical experiment we can test, and it ran everywhere at once. It also ran under conditions we can model with nuclear reaction networks, cross-sections, and a rapidly changing temperature. The key is timing, because the universe is expanding while reactions try to run. Temperature drops fast, densities fall, and the nuclear window closes before heavier elements can form. The cosmos cools like a rapidly expanding oven, hot enough to fuse briefly, then too thin and too cold to keep going. In plain terms, The universe loses its ability to keep nuclei colliding before it can climb to carbon and beyond. At first, even deuterium cannot survive, because energetic photons break it apart as soon as it forms. This deuterium bottleneck delays the assembly of heavier light nuclei until the temperature falls enough for deuterium to persist. Once that bottleneck clears, reactions proceed quickly, but only for a short span. The bottleneck is a reminder that nuclear binding energy matters as much as temperature, because survival is a competition between formation and destruction. Primordial ratios depend on baryon density, because density sets collision rates and reaction pathways. They also depend on the expansion rate, because expansion sets the clock. A denser universe builds nuclei more efficiently, while a faster expanding universe shuts the factory down sooner. These dependencies are not vague. They are encoded in how reaction rates scale with number density, and in how the Hubble rate scales with energy density. Neutrons are especially sensitive to that clock, because free neutrons decay. If expansion is faster, more neutrons survive to become helium, and helium-4 increases. If expansion is slower, more neutrons decay before they can be captured, and the helium fraction falls. The neutron lifetime, measured in laboratories, becomes a cosmological input, an earthly number that echoes into the first minutes. There is a simple, almost poetic outcome here. Helium-4 is favored because it is tightly bound, and once nucleosynthesis begins in earnest, neutrons get locked into helium quickly. That is why the primordial helium fraction is robust, roughly a quarter of the baryonic mass, across a wide range of plausible conditions. The universe, in effect, finds the most stable light nucleus available and piles neutrons into it before the window closes. Deuterium is the fragile marker because it is easily destroyed later in stars. Measuring deuterium in pristine gas tests the early conditions with unusual precision. Astronomers search for ancient, low metallicity clouds that have not been processed by stellar interiors, because those clouds preserve the early ratio. In practice, they look for deuterium's slight spectral offset in absorption lines, a tiny shift that becomes a major cosmological constraint. Helium-3 sits in a more complicated middle ground because it can be both made and destroyed inside stars. That makes it a less clean probe, yet it still provides a consistency check. Even lithium, though scarce, matters because it is sensitive to details of reaction pathways and to the thermal history. Together, these elements form a chemical ledger, and the early universe balanced it in minutes. Lithium adds a quieter complication that has become historically important. Standard calculations predict a primordial lithium abundance that is higher than what we infer from the oldest stars, a mismatch known as the lithium problem. It may reflect subtle astrophysics in stellar atmospheres, or it may hint at missing early universe details. The tension has persisted for decades, which is why it remains a live question rather than a footnote. So minutes after the beginning, the universe has already chosen its basic chemical inventory. That choice is a measurable constraint on any story about the earliest times. It is also a reminder that cosmology is not only geometry and expansion, it is nuclear physics running under extreme conditions. The remarkable part is that the predictions and the measurements still meet, within uncertainties across vast spans of time. Now compress the timeline further, because the next milestones arrive in seconds. The universe is no longer a place where nuclei are stable, but a thermal bath of particles. Temperatures are measured in billions of Kelvin, and energy is better described in electron volts than in degrees. When we talk about heat here, we really mean typical particle energies, set by the temperature of an almost perfectly mixed plasma. In the first seconds, neutrinos decouple from the plasma as weak interactions fall behind expansion. From then on, neutrinos free stream, carrying energy that still affects later observables. They become a cosmic background in their own right, nearly impossible to detect directly, yet gravitationally influential. The decoupling is a freeze-out process, where interaction rates drop below the Hubble expansion rate and the particles stop exchanging momentum efficiently. Neutrino decoupling matters because it changes how energy is partitioned between species. It also changes the expansion rate, which feeds back into nucleosynthesis yields. In practice, we encode this in an effective number of relativistic species, a parameter that the CMB and element abundances can constrain. If that number were measurably higher, it would imply extra light particles, and it would rewrite part of the early particle census. Soon after, electrons and positrons annihilate as the temperature drops below their rest mass. Their energy reheats the photon bath, leaving neutrinos slightly cooler than photons. The result is a specific temperature ratio between photons and neutrinos, a relic of this annihilation that persists to the present. This is one of those early universe events that sounds dramatic, yet it is governed by equilibrium thermodynamics and simple counting of degrees of freedom. That temperature difference is not a detail, because it is measured indirectly in the CMB and in nucleosynthesis. It is one of the ways we test the particle content of the early universe. If extra light particles existed, they would subtly change the expansion rate and shift these well-measured outcomes. The universe would cool differently, and the light element factory would close on a different schedule. At this stage, the universe is a particle soup, close to thermal equilibrium. Photons, electrons, positrons, neutrinos, and baryons interact in a dense, rapidly cooling plasma. The dominant behavior is statistical. Populations of particles constantly created and destroyed, tracking the temperature like a living census. When the temperature drops below a particle's mass, the census changes, and the universe's effective heat capacity shifts. To visualize it, imagine a bright, uniform fog where no object can cast a shadow. Every point is flooded with radiation, and every charged particle is buffeted by collisions. The universe is not empty space with things in it, yet it is a coupled fluid of energy and matter. If you could freeze a frame, you would not see objects, only a restless glow with fleeting particle identities. Rewind further into fractions of a second, and even protons and neutrons stop being meaningful. The building blocks of familiar matter dissolve into a more primitive state. The labels we use in everyday physics fail because the relevant degrees of freedom have changed. What we call a proton is not fundamental. It is an emergent bound state, and bound states do not survive unlimited heat. At microseconds, the universe is hot enough that quarks and gluons are not confined into hadrons. Matter exists as a quark. Gluon plasma, a phase we can hint at in heavy ion collisions. In laboratories, we recreate tiny droplets of this state at facilities like RHIC and the LHC, then infer its properties from the debris. Those droplets are microscopic and short-lived, yet they teach us that the quark, gluon plasma, behaves less like a dilute gas and more like a strongly coupled fluid. Confinement is the rule change here, because it is not just a new particle list. When the universe cools through the QCD transition, quarks become locked into hadrons, and the effective degrees of freedom drop. That drop changes how the energy density scales with temperature, which in turn affects the expansion rhythm. Even the sound speed of the cosmic medium changes, and that can leave subtle imprints on later evolution. Hadronization is not merely assembly, but a phase change in how the strong force behaves. The same underlying theory is there, yet the emergent behavior is radically different. Above the transition, quarks roam in a collective medium. Below it, They are trapped inside protons and neutrons as if behind an invisible wall. The wall is the growth of the strong coupling at low energies, which makes isolated quarks energetically forbidden. The visual here is striking if we let it be. A seething, near-uniform plasma cools until structure becomes possible, not as galaxies yet, but as stable composite particles. It is the first time the universe can meaningfully count baryons as distinct objects, rather than as a shared field of constituents. In a cinematic sense, this is where the cast of characters becomes recognizable, even though the stage is still blindingly hot. This is a pattern we will keep seeing as we approach the beginning. The closer we get, the more the universe is described by fields and symmetries, not by objects. What looks like a thing at low energy becomes a collective behavior at high energy, a change in language as much as a change in substance. Each step backward is a reminder that our everyday categories are not eternal, they are phase-dependent. Now push back to around 10 to 12 seconds, the electro-weak epoch. At these energies, the electromagnetic and weak forces are unified in a single electro-weak symmetry. The separation we learn in school is a low-energy story, like ice and water being different phases of the same molecule. Here, the phase is not matter's arrangement, but the vacuum's symmetry state. In that symmetric phase, the distinction between photon and W and Z bosons is not the one we know. The force carriers are different mixtures, and the rules are written in the symmetry. The interactions are governed by gauge fields that behave as if the universe has not yet chosen which direction electromagnetism will point. What later becomes a massless photon is, at this stage, part of a unified set of fields. As the universe cools, the Higgs field takes on a non-zero value everywhere. That symmetry breaking reshapes the particle spectrum and gives masses to W and Z bosons. It is often described as a field turning on, but more precisely, it is the vacuum state changing to a lower energy configuration. The Higgs field is present throughout. What changes is the state it settles into as temperature drops. The Higgs mechanism also gives masses to fundamental fermions through their couplings. Mass here is not a substance added later, but an interaction with a field-filling space. Some particles couple strongly and become heavy. Others couple weakly and remain light, and that hierarchy shapes everything that follows. Without that hierarchy, chemistry and stable atoms would look radically different, or might not exist at all. Historically, this idea matured over decades, and it was not always accepted as inevitable. The electroweak theory was built in the 1960s, and the Higgs mechanism was proposed to preserve consistency while allowing massive force carriers. The Higgs boson's discovery in 2012 did not end the story, but it anchored this part of the timeline to experimental reality. It also reminded us that cosmology is tethered to accelerators, because the early universe once reached energies we now reproduce in controlled bursts. This is where the narrative tension sharpens, because the universe is becoming less like matter. What we call particles are excitations of fields, and the fields are defined by symmetry. The familiar solidity of objects is nowhere to be found, replaced by a shifting landscape of quantum states. The deeper we go, the more stuff becomes a set of transformation rules, rather than a collection of things. Yet one of the biggest questions is already active in this era, and it still has no settled answer. If high energies create matter and antimatter in pairs, why is anything left? The question is not rhetorical. It is a quantitative crisis, because symmetry would predict a universe with almost no atoms. In a perfectly symmetric outcome, matter and antimatter would annihilate efficiently, and the cosmos would be a thin bath of photons with no chemistry. The baryogenesis puzzle is the question of why there is more matter than antimatter. If the early universe were perfectly symmetric, Matter and antimatter would annihilate into radiation, leaving almost no atoms. The fact that we exist implies a tiny excess of matter survived the annihilation era, and that excess became everything we see. The problem is not that asymmetry exists, but that it is so specific, small, and yet universal. We know the asymmetry is small but decisive, roughly 1 extra baryon per billion photons. That tiny imbalance becomes every galaxy, every star, and every observer asking why. It is a cosmic accounting error that never corrected itself, and the universe has been living with the consequences ever since. The CMB's photon density, measured precisely, makes that statement numerical rather than metaphorical. Sakharov conditions define what any successful baryogenesis mechanism must satisfy. Baryon number violation must occur, C and CP symmetries must be violated, and the universe must be out of thermal equilibrium. These are not optional features. They are the minimal ingredients needed to turn symmetric laws into an asymmetric outcome. Without out-of-equilibrium evolution, detailed balance would erase any net excess as fast as it formed. CP violation is the clue we can measure in laboratories, but known sources seem too weak. That gap suggests new physics or new dynamics, or a deeper accounting of early transitions. It is one of the places where particle physics and cosmology meet, and neither side can solve it alone. The mystery is sharpened by the fact that we do see CP violation in certain decays, which proves the door is not locked, yet it may not be open wide enough. Some proposals place baryogenesis near the electro-weak transition, where out-of-equilibrium conditions might arise. Others place it at much higher energies, tied to grand unification or heavy particle decays. Each proposal has a different signature, and each must respect the constraints we already extracted from the CMB and primordial abundances. The early universe is not a blank canvas. It is a constrained system, and every new mechanism must fit inside the measured frame. Either way, baryogenesis exposes a theme that matters for our central question. The early universe is not just hot, it is a machine that selects outcomes from symmetric possibilities. It takes laws that look reversible and produces a world with a preferred sign, more matter than antimatter, and therefore a future with chemistry. That preference is subtle, but it is the difference between a universe that can host observers and one that can't. Now the timeline becomes almost abstract because we approach energies where our tested theories stop agreeing. We are heading toward the Planck epoch, around 10^43 seconds. Here the units themselves feel alien because the characteristic scales are built from gravity, quantum mechanics, and the speed of light. Planck time is not chosen for convenience. It is the time you can form when you combine those constants, as if nature is telling us where classical intuition breaks. General relativity describes gravity as the curvature of space-time, and it works superbly at accessible scales. Quantum field theory describes particles and forces as quantized fields, and it works superbly in laboratories. We trust both frameworks because they have survived decades of experimental pressure, yet they are written in different mathematical languages. One treats space-time as a smooth geometry, while the other treats fields as operators with inherent fluctuations. But at the Planck scale, the two frameworks collide. Quantum fluctuations of space-time itself should matter, yet general relativity treats space-time as a smooth, classical geometry. If space-time can fluctuate like other fields, then the notion of a single, well-defined geometry becomes questionable. Even the concept of distance becomes probabilistic, and the clean background we rely on may dissolve into a quantum texture. If we extrapolate classical general relativity backward, the scale factor goes to zero and densities diverge. That mathematical blow-up is what we call a singularity. It appears not because we have observed it, but because the equations, pushed beyond their tested domain, produce an infinity. The singularity is a warning light on the dashboard, not a photograph of a real place. A singularity is often misheard as a physical object, like a point of infinite stuff. In physics, it is usually a signpost that the theory has run out of valid instructions. It tells us that important effects, likely quantum gravitational ones, have been neglected, and the neglected terms are no longer small. When a calculation yields infinity, it is often the universe telling us our approximation has become illegal. Think of it like a map that ends at the edge of the paper. The blank margin does not prove the world ends, it proves the map is incomplete. The singularity is that blank margin, and our job is to decide what new cartography replaces it. The honest stance is not despair, but caution, because the map has been reliable until the ink runs out. So the Big Bang singularity is not automatically the first moment of reality. It is the boundary where our equations stop being trustworthy without quantum gravity. The honest statement is not, "We know there was a singularity," but "Our current description cannot be extended without new principles." That distinction matters because it leaves room for scenarios where the earliest state is finite, or where time behaves differently than we assume. Quantum gravity is not a single finished theory we can simply plug in. It is a research frontier, with candidates like string theory and loop quantum gravity, and with open questions about what spacetime even is. Some approaches treat spacetime as emergent from deeper quantum degrees of freedom, which would make the earliest time a derived concept. If time is emergent, then asking what happened before time may be like asking what is north of the North Pole. This is why the cause question becomes difficult in a technical way, not only a philosophical one. Causes are defined within time, yet time is part of the system whose earliest behavior we cannot reliably compute. When the stage itself becomes dynamical and possibly quantum, the ordinary grammar of before and after can break. We may need a description where causality is approximate, or where it emerges only after the universe cools into a classical spacetime. As we approach the Planck epoch, the timeline itself becomes a hypothesis. We can label times by extrapolating known laws, but we cannot guarantee those labels remain meaningful. The numbers still guide our intuition, yet they may be coordinates on a map that changes its geometry near the edge. That is an unsettling thought, because it suggests our neat sequence of epochs may be a low-energy projection of a deeper structure. Even the word before becomes unstable, because it assumes a background ordering that may not exist. If time emerges from deeper physics, then earlier may be an approximate concept, not a fundamental one. That possibility is unsettling, because it suggests our deepest questions might require a new kind of explanation. What would it mean to explain an origin without relying on temporal sequence? And would we recognize such an explanation as satisfying? Still, we do not stop here, because cosmology has one more move that tries to extend the story. It invokes a bold idea that changes what the earliest timeline could look like. The move is not a retreat from evidence, but an attempt to explain patterns that otherwise look like improbable coincidences. It is an effort to replace fine-tuned initial conditions with a dynamical process that naturally produces what we observe. To go earlier than our timeline allows, cosmology invokes a burst of accelerated expansion. Inflation may be our bridge across the missing physics, or it may be another layer of mystery. It is a proposal about dynamics, about what the universe did, not merely a label for ignorance. In the inflationary picture, the expansion rate is driven by an energy component with negative pressure, which makes gravity act repulsively on large scales. Inflation is not introduced as a decorative twist, but as an attempt to explain specific puzzles. It aims to explain the universe's near flatness, its large-scale uniformity, and the origin of primordial fluctuations. Without something like inflation, regions of the CMB that look nearly identical would have had too little time to exchange signals and equilibrate. The horizon problem is, at heart, a mismatch between the size of the observable sky and the distance light could have traveled in a simple extrapolation. Flatness is another puzzle with a technical edge. In classical expansion without inflation, spatial curvature tends to grow in relative importance unless it is tuned extremely close to zero early on. Inflation changes that evolution by stretching space so dramatically that any initial curvature becomes diluted, leaving the universe looking nearly Euclidean. It is as if the surface of a small sphere were inflated until, locally, it appears flat. If inflation happened, it would push quantum fluctuations to cosmic scales and seed structure. It would also stretch space so rapidly that regions now far apart were once in causal contact. In that picture, the tiny irregularities in the CMB are not noise. They are amplified quantum uncertainty, turned into the scaffolding for galaxies. The same quantum jitter that normally lives at subatomic scales becomes, through expansion, a pattern written across the sky. The visual implication is almost paradoxical. A minuscule patch of space, smaller than an atom, expands to astronomical size in a fraction of a second. Yet the expansion is of space itself, not an explosion into pre-existing emptiness. The universe does not expand into something. The distances inside it grow, and light has to chase a moving target. If you visualize a grid painted on space, inflation stretches the grid, and the stretching is what changes separations. But inflation also raises new questions about beginnings, because it needs initial conditions of its own. It can move the boundary, but it may not eliminate the need for a deeper origin story. If inflation is driven by a field, we must ask why that field was in the right state, and why it began when it did. Even in an inflationary universe, the question of why these conditions can reappear one step earlier, waiting at the new edge of the map. So Chapter 3 ends with a sharpened dilemma, not a resolution. The farther back we go, the more the universe becomes fields, symmetries, and phase changes, and the less our everyday causality applies. The story remains coherent, but it becomes less like a narrative of objects and more like a sequence of rule changes. Each rule change is constrained by data, yet each also opens a door to deeper unknowns. The central question remains, now with a clearer technical edge. If the Big Bang marks the origin of our observable universe, what caused it, and what does nothing mean when time is part of the universe? When our best theories treat time as dynamical, the question of what came first becomes a question about the origin of the ordering itself. And if ordering is emergent, then perhaps the deepest explanation will sound less like a cause and more like a consistency condition. In the next chapter, we follow inflation into its promises and its costs. We ask what it explains, what it predicts, and whether it truly reaches toward a beginning or only redraws the edge of the map. And we keep watching the data, because in cosmology, the universe is always leaving clues, even when it refuses to show us the whole scene. We have traced the universe back to a hot, dense plasma and a boundary of tested physics. Now we ask what could set the initial conditions that the CMB seems to assume. The camera pulls away from the afterglow itself, an all-sky shell of microwaves, until the question feels less like astronomy and more like origin. The hot Big Bang explains how the universe evolves once it is already expanding and thermal, with particles colliding often enough to share a common temperature. It gives us a clock, a cooling curve, and a sequence of well-tested transitions in the early plasma, from quark confinement to nucleosynthesis. It does not automatically explain why distant regions look so similar, as though they rehearsed the same script before they ever met. The CMB is uniform to about 1 part in 100,000 across the sky. That number is not poetic. It is a quantified smoothness measured by satellites that mapped temperature to microkelvin precision. Missions like COBE first revealed the anisotropies, and later WMAP and Planck turned them into a detailed statistical map, almost a fingerprint. In that map, the mottling is tiny, yet it is also the earliest photograph we possess. In a simple, non-inflationary timeline, many of those regions were never in contact, so they had no time to trade heat or information. Light travels at a finite speed, and the early universe has a finite age, so there is a limit to what can be causally coordinated. When we look at the CMB, we are seeing the universe at recombination, about 380,000 years after the start of the hot phase. At that moment, the observable sky is a sphere of emission, and its opposite sides appear to agree too well. Recombination is not a sudden switch, but a brief era when electrons finally bind to protons and helium nuclei, making neutral atoms and thinning the fog. The process depends on atomic physics, binding energies, photon densities, and the expansion rate, so it unfolds over a range of redshifts rather than a single instant. Photons stop scattering constantly and begin free streaming, so the universe becomes transparent in a way it was not before. That surface of last scattering is therefore a time slice, and it carries both temperature and polarization information. The polarization is not an afterthought because it encodes the geometry of scattering. A quadrupole pattern in the local radiation field imprints a preferred direction on the outgoing light, and that directional memory survives as faint, linear polarization. When we map that polarization, we are effectively mapping how the plasma moved and how gravitational potentials shaped the light. Even the quietest parts of the sky carry a record of motion. The horizon at recombination is too small to coordinate the whole CMB, so the uniformity looks like a coincidence written into the initial state. Visually, imagine the last scattering surface as a glowing sphere around us, faintly mottled like a peach's skin under soft light. Now divide that sphere into patches, each patch the size of the horizon at that time. Each patch could have equilibrated internally, yet the patches should not have agreed with one another. In the basic picture, those patches are like islands separated by oceans of no contact, yet they share nearly the same temperature to astonishing accuracy. The puzzle is not that each island is internally smooth, because local interactions can do that. The puzzle is why islands that never exchanged a single photon of thermal information still agree on the same baseline temperature. It is as if thermometers on distant shores all read the same value, despite no shared weather. This is the horizon problem, and it is not a complaint about measurements. It is a mismatch between causal contact and observed uniformity, between what could have equilibrated and what appears already equilibrated. The tension is conceptual. The universe seems to remember a common past that the simplest timeline cannot provide. We are forced to ask whether the timeline is incomplete or whether our intuition about contact needs revision. There is a second mismatch, and it hides inside the word flat. The universe appears very close to spatially flat on the largest scales, meaning its geometry is nearly Euclidean when we draw huge triangles across cosmic distances. In general relativity, spatial curvature is not just a shape. It is a term in the Friedmann equations that competes with matter and radiation as the universe expands. Curvature behaves like an effective energy component with its own scaling, and that scaling makes it dangerous. Curvature can be positive, like a sphere, or negative, like a saddle, and each case changes how volumes and angles behave. Observationally, we infer curvature by combining the CMB's angular scale with distance measurements, effectively asking how big a standard ruler looks across the sky. That ruler is set by the sound horizon, the distance acoustic waves could travel in the primordial plasma before recombination. The answer keeps coming back, close to flat, within tight error bars. In standard expansion, curvature becomes more important with time unless it starts extremely tiny. That statement is technical, but the intuition is simple. Small early departures from flatness tend to grow into large late departures. Near flatness, therefore, looks like a finely tuned initial condition, as though the early universe balanced on a knife edge and never fell. The more we tighten the error bars, the sharper the knife edge becomes. This is the flatness problem, and it is a stability problem. Small deviations from flatness grow rather than self-correct, so the present-day near flatness implies an extremely special early ratio of curvature to total energy density. The closer we measure the universe to flat today, the more delicately it seems to have been set long ago. We are not merely measuring geometry, we are measuring a sensitivity to beginnings. A third puzzle comes from particle physics expectations. Many high-energy theories predict relics like magnetic monopoles, topological defects that can appear when symmetries break as the universe cools. The visual here is a phase transition, like ice forming in water, where different regions choose different orientations and defects are left where the choices cannot be smoothly reconciled. In a cosmic setting, the cracks are not in ice, but in fields. In field theory language, the vacuum manifold can have non-trivial topology, and that topology makes defects not merely possible, but generic. Monopoles are one example, but the broader point is that early universe symmetry breaking can leave behind stable knots in the field configuration. Once formed, those knots are difficult to unwind without dramatic dynamics. They are protected by topology, which is a mathematical way of saying they cannot be gently erased. Monopoles would be heavy, stable, and hard to erase once produced. In grand unified theories, they can be so massive that even a tiny number would matter gravitationally, and they would roam the cosmos as unmistakable fossils of early symmetry breaking. Yet the universe shows no convincing sign that they exist. Despite searches in cosmic rays, lunar samples, and detector experiments. The silence is striking, because the theories that inspired monopoles were not fringe ideas. This absence is not proof of inflation, but it is pressure. It suggests the early universe did not simply cool from arbitrarily high temperatures in equilibrium, producing every relic that high-energy physics might allow. Something about the early story either avoided making monopoles or diluted them to near nothingness. The question becomes practical. What mechanism could do that without breaking everything else we trust? Inflation was proposed as a single dynamical move that addresses all three tensions. Historically, the idea emerged in the early 1980s, when cosmologists and particle physicists were trying to connect the Big Bang to symmetry breaking and high-energy fields. Alan Guth's original proposal was sharpened and reshaped quickly. New versions solved issues in the first drafts, and the concept matured in real time. Within a few years, old inflation gave way to new and chaotic variants, each adjusting how the exit could work. It is a short era of accelerated expansion before the hot Big Bang phase, a prelude that changes the initial conditions rather than rewriting later successes. The camera language shifts accordingly. We are no longer watching a cooling fireball, but a stage being built before the curtain rises. The set is space-time itself, and the construction happens at a pace that feels almost impossible. In inflation, the scale factor grows nearly exponentially for a brief time. Distances double, then double again, while the clock barely advances, and the universe's size can increase by an enormous factor in a tiny fraction of a second. The visuals shift from a calm expansion to a sudden time lapse, grid lines racing outward as though space-time itself is being unspooled. A region smaller than an atom can be stretched to astronomical size, at least in principle. The key ingredient is an energy component that behaves like vacuum energy. It has nearly constant density and negative pressure, which sounds abstract until we translate it into the equations that govern expansion. In general relativity, pressure gravitates, not just mass and energy density, so the sign and magnitude of pressure can change the cosmic acceleration. The vacuum-like state acts as a fluid with equation of state close to W equals -1. Negative pressure can drive accelerated expansion of space. In the Friedmann acceleration equation, a sufficiently negative pressure makes gravity effectively repulsive on large scales, not by pushing matter outward, but by changing how the metric evolves. The result is not a blast wave. It is a smooth, relentless swelling of distances. It is expansion as geometry, not expansion as debris. This is not an explosion of matter into pre-existing emptiness. It is the metric itself stretching, changing the meaning of distance, and turning a tiny region into something vast without needing matter to stream through space. If we could watch rulers embedded in space, they would lengthen everywhere at once, even where no particles are present. The emptiness is active, and the activity has a precise mathematical form. During inflation, space can expand so fast that 2 points separate faster than light. That does not violate relativity because no object locally outruns a light beam, and no signal is sent faster than light through its immediate neighborhood. The superluminal effect is global, an increase in separation rather than local motion. The local laboratory still sees the same speed limit, even as the cosmic map stretches. Relativity forbids superluminal motion through space, not superluminal growth of space. Causality remains local, even when global distances inflate. So each observer still sees nearby physics, obeying the same speed limit. The strange part is that the distance between faraway observers can grow faster than any signal could cross it. Inflation exploits that distinction, and it makes it central. Inflation solves the horizon problem by changing what counts as far. Our entire observable universe can originate from a tiny, causally connected patch, small enough that light and particles had time to interact and smooth out gradients. The patch is not special by location. It is special because inflation makes its later size enormous. The uniformity is not imposed at the end, but inherited from an earlier intimacy. Before inflation ends, that patch is small enough for interactions to smooth it, and even small temperature differences can be erased by rapid scattering. After inflation, it is stretched beyond the horizon, carrying its uniformity outward, like ink spread thin across a page until it covers a continent. The uniform temperature of the CMB then becomes a memory of that earlier contact. We see agreement across the sky because the sky once fit inside a single causal neighborhood. Inflation solves the flatness problem by dilution. Curvature scales differently than vacuum-like energy, and exponential expansion drives curvature toward zero, in the same way rapid stretching makes any initial bend look negligible. In the equations, the curvature term becomes tiny compared with the dominant vacuum-like component. What was once a meaningful deviation becomes a rounding error. A curved surface looks flatter when magnified enough. Inflation magnifies the geometry until any initial curvature becomes observationally negligible. So the universe we measure today naturally appears close to flat. The flatness is not enforced by hand. It is produced by the dynamics of accelerated expansion. The universe does not balance on a knife edge because the knife edge is stretched into a plane. Inflation also dilutes unwanted relics. Any monopoles or other heavy defects become exponentially rare per observable volume, because their number density drops as space expands, while the vacuum-like energy stays nearly constant. Even if monopoles were once common, inflation can make them effectively absent in our entire visible region. The fossils are not destroyed, but they are pushed so far apart that we may never encounter one. These are the selling points, and they are powerful. They turn apparent fine-tuning into an outcome of dynamics, replacing an unexplained initial arrangement with a process that drives the universe toward a particular state. Yet a good solution must do more than smooth. It must also explain the small imperfections that later become everything we see. A universe that is too perfect would be sterile, but inflation is not just smoothing, and the story turns on a paradox. Inflation must also create the tiny irregularities that later become galaxies, clusters, and the web-like structure traced by surveys. The universe is uniform, yet not perfectly uniform, and that slight imperfection is not a flaw. It is the seed of complexity. The same process that erases large gradients must preserve, and even generate, a controlled speckle. The CMB anisotropies and large-scale structure require primordial perturbations with specific statistics. They must have the right amplitude, about 1 part in 100,000, and they must be correlated across angles in a way that matches the acoustic peaks in the CMB power spectrum. Those peaks are not decorative. They encode sound waves in the early plasma, frozen into a sky map. The pattern is a fossil of pressure fighting gravity, oscillation by oscillation. Inflation offers a mechanism that is both minimal and strange. Quantum fluctuations in fields become classical density variations after being stretched beyond the horizon, turning microscopic uncertainty into macroscopic structure. The visuals here are almost surreal. Tiny jitter in an invisible field, then a sudden stretching until the jitter becomes a cosmic blueprint. A random tremble becomes an architectural plan. In quantum field theory, even the vacuum is not quiet. Fields fluctuate around their lowest energy state, producing temporary variations in amplitude, because the uncertainty principle forbids a perfectly still ground state. These fluctuations are not particles in the ordinary sense, but they can become real excitations when the background changes rapidly. The vacuum is a sea with ripples, even when nothing seems to move. Normally, those fluctuations live on microscopic scales and average away. In a non-inflating universe, they remain tiny, oscillatory, and locally cancelling, like ripples that never grow beyond the surface of a pond. Inflation stretches their wavelengths until they become macroscopic and effectively frozen, because the expansion outruns the ability of microphysics to keep them in causal contact. The wave stops behaving like a wave and starts behaving like a fixed offset. When a mode is stretched beyond the Hubble radius during inflation, causal microphysics cannot keep it oscillating. Its amplitude becomes an imprint, a perturbation in the curvature of space-time, and the density of whatever will later become the hot plasma. The phrase "beyond the Hubble radius" is the technical marker for when the mode stops behaving like a normal wave. It is not that physics shuts off, but that communication across the wavelength becomes impossible. Later, when the universe expands and the Hubble radius grows, those modes re-enter. They return as real perturbations in density and curvature, now able to influence the motion of matter and radiation. The universe then treats them as initial conditions for gravitational collapse, acoustic oscillations, and the eventual formation of galaxies. A pattern that was once stretched outside causal reach comes back inside, like a message returning after a long delay. This is the quantum origin story that inflation makes testable. Structure begins as vacuum noise, promoted to cosmic scaffolding by expansion, and then refined by gravity over billions of years. It is a remarkable inversion of scale. What begins as the smallest possible fluctuation becomes the largest visible pattern. When we see the cosmic web, we may be seeing the magnified residue of quantum indeterminacy. The result is a spectrum of perturbations that is nearly scale invariant. That means fluctuations have almost the same strength across many length scales, so no single scale is privileged as the only seed size. Visually, the power spectrum is a nearly flat line when plotted in the right variables, with a slight tilt that carries deep information. That slight tilt is the whisper of changing conditions during inflation. Scale invariance is not exact, and the deviation is a measurement target. The spectral index NES quantifies the tilt away from perfect scale invariance, and its value tells us about how slowly the inflaton field rolled and how the inflationary energy changed over time. A perfectly constant vacuum energy would give one limit, while realistic models predict a small departure. The tilt is a way of reading the inflaton's motion without ever seeing the field directly. Observations find n-S slightly less than 1, consistent with many slow-roll inflation models. This is one of inflation's strongest empirical supports, because it is not just a qualitative match, but a quantitative one, extracted from the angular pattern of the CMB. The universe is almost, but not exactly, scale-free, and almost that matters. It is a controlled imperfection, and it points to dynamics rather than pure coincidence. The perturbations are also close to Gaussian. That means their statistics are well described by a two-point correlation function and a power spectrum, much like how random noise can be summarized by its variance and correlations. In a Gaussian field, the peaks and valleys are distributed in a specific symmetric way, and higher-order patterns are suppressed. The CMB map looks like a random field, but a very particular kind of random field. Non-Gaussianity would reveal interactions or multiple fields during inflation. It would show up as subtle correlations among triples or quadruples of points in the CMB, beyond what a simple Gaussian random field predicts. Current limits already rule out many simple alternatives to single-field slow-roll behavior, tightening the space of plausible inflationary dynamics. The absence of strong non-Gaussianity is itself a clue, because nature could have chosen otherwise. Inflation also predicts gravitational waves from quantum fluctuations of space-time itself. These tensor modes are not vibrations in matter, but ripples in the metric, generated by the same quantum principles that produce scalar density perturbations. If they exist at an observable level, they would be a direct window onto the energy scale of inflation. They would also be a rare test of quantum gravity in its gentlest, most indirect form. The cleanest signature would be primordial B-mode polarization on large angular scales. It would be a fossil of inflationary gravitational waves, encoded in a swirling pattern of polarization that cannot be made by simple density perturbations alone. The visuals shift to polarization vectors across the sky, curling into faint pinwheels. The signal is subtle, and the universe does not make it easy to isolate. The tensor-to-scalar ratio R measures the relative strength of those tensor modes. A detection would pin down the energy scale of inflation, because stronger gravitational waves generally imply a higher inflationary energy density. It would also constrain the inflaton's field range, linking cosmic data to the geometry of the potential. In that sense, R is not just a number, but a bridge between sky maps and high-energy theory. So far, R has only upper limits, and those limits are tightening. The absence of detection does not kill inflation, but it narrows its viable models, pushing theorists toward potentials that predict smaller tensor signals. Each new limit is like a chisel stroke, carving away at the landscape of possibilities. The remaining models must fit into a smaller and smaller corridor. Foregrounds complicate the search, especially polarized dust in our galaxy. Dust grains align with magnetic fields and emit polarized light, creating patterns that can mimic the sought-after signal if not carefully separated. Experiments must therefore map the sky at multiple frequencies, because dust and primordial signals scale differently with wavelength. The visuals here are layered maps: one sky, many colors, and a careful subtraction. Lensing also creates B modes by distorting E modes. As CMB photons pass through the gravitational fields of galaxies and dark matter, their paths bend slightly, converting some polarization patterns into the B mode type. Delensing can subtract that contribution, but it demands high sensitivity and careful modeling of the intervening mass distribution. Even the late universe leaves fingerprints on the early one, and those fingerprints must be removed. These tests matter because inflation is flexible. If it can be tuned to fit almost anything, then its predictions must be sharpened by data, and the most valuable data are those that are hardest to imitate. The goal is not to protect inflation as an idea, but to force it into a corner where it must either succeed specifically or fail clearly. Precision becomes a form of skepticism. To understand inflation's flexibility, we need its basic engine. Most models use a scalar field called the inflaton, a field value that fills space and can vary slowly in time. A scalar field is the simplest kind of field, just a number at each point. But in cosmology, simplicity can have enormous consequences. A single degree of freedom can control the fate of horizons, curvature, and structure. The inflaton has a potential energy landscape that determines how it evolves. When potential energy dominates over kinetic energy, the expansion accelerates, because the energy density behaves almost like a cosmological constant. The shape of the potential controls how long inflation lasts and how gently it ends. In visual terms, the field is a ball rolling on a plateau, and the plateau must be wide enough to matter. In the slow roll picture, the field changes gradually, while the energy density stays nearly constant. That near constancy is what sustains quasi-exponential expansion, and it also ensures that the perturbations produced are nearly scale invariant. Technically, slow roll parameters quantify how flat the potential is, translating geometry in field space into observable numbers. A small change in slope becomes a measurable tilt on the sky. The shape of the potential sets observable parameters. It influences NHS, R, and possible non-Gaussianity through the dynamics of the field, and it determines how the expansion rate changes from moment to moment. In this way, a curve drawn in an abstract potential diagram becomes a prediction for patterns on the sky. The universe becomes a detector for the shape of an unseen function. Here, the chapter's tension deepens. We do not know what the inflaton is in particle physics terms, and that ignorance is not a minor detail. The inflaton could be a new fundamental field, a composite effective degree of freedom, or a familiar field pushed into an unfamiliar regime. Each possibility changes what we should expect about couplings, symmetries, and quantum stability. It could be a new field, a known field in an unusual regime, or an effective description of deeper physics. Each option carries different assumptions about symmetries, couplings, and the validity of effective field theory at extremely high energies. The visuals here are layered, particle physics diagrams fading into cosmic expansion, as if the micro and macro are negotiating a treaty. Behind the smooth sky map, there may be complicated ultraviolet bookkeeping. We also do not know why the potential has the required form. Many potentials can produce inflation, and many are hard to motivate from fundamental theory, especially when quantum corrections threaten to spoil the flatness needed for slow roll. The inflaton potential must be stable against the very quantum effects that make inflation's perturbations possible. The theory must balance on a ridge, and quantum loops keep trying to reshape the ridge. Even if a potential is chosen, initial conditions remain a problem. Why did the inflaton start high enough and smooth enough to inflate our patch, rather than rolling too quickly or starting in a state dominated by gradients and kinetic energy? The question is not whether inflation can happen, but how naturally it begins in a realistic early universe. If the universe began messy, how did a clean inflating domain ever form? Inflation was introduced to reduce fine-tuning in the hot Big Bang initial conditions. Yet it can reintroduce fine-tuning in the inflationary setup, depending on the model and on how we define generic starting states. The narrative tension is subtle. One kind of specialness is traded for another, and the trade must be judged carefully. We gain a mechanism, but we inherit a question about the mechanism's own plausibility. Some argue inflation is an attractor, meaning it starts under broad conditions. In that view, expansion damps away inhomogeneities and kinetic energy, pulling the system towards slow roll like friction, pulling a pendulum toward rest. Others argue it needs special starting points, depending on the model, because too much initial disorder can prevent a smooth inflating patch from forming. The debate is technical, yet the intuition is familiar. Does order emerge easily or only under rare circumstances? This is where the cause question shifts rather than disappears. If inflation happened, what caused inflation to begin, and what set its vacuum-like energy in the first place? We can describe the mechanism once it is underway, yet the ignition still feels like a missing scene. The story explains the fast forward, but not who pressed the button. Inflation also must end, or the universe never becomes the hot plasma we observe. Ending inflation requires the inflaton to leave the slow roll regime, which means the potential must steepen, or the field must reach a region where its motion changes character. The graceful exit is not optional. It is the bridge back to the tested Big Bang sequence. Without an exit, there is no CMB, and there are no atoms. When the field reaches a steeper part of its potential, it accelerates and begins oscillating. The vacuum-like energy then converts into particles, either through perturbative decays or through explosive, non-equilibrium processes that can rapidly populate other fields. The visuals shift from smooth expansion to a sudden fireworks of particle production, though the fireworks are quantum fields filling space. Energy that once looked like empty vacuum becomes a crowded bath of excitations. This conversion is called reheating, and it is the bridge to the hot Big Bang. It fills the universe with a thermal bath of radiation and matter, resetting the cosmic conditions so that nucleosynthesis, recombination, and later structure formation can proceed. Reheating is the moment the universe becomes hot again, but now with a vastly expanded size. The temperature is reborn, but the stage is much larger. The physics here can be subtle, because reheating may begin with a violent preheating stage, where resonances amplify field fluctuations. Energy can pour into other species in bursts, creating a far from equilibrium soup before true thermalization sets in. In plain terms, the universe may heat up in fits and starts, not in a single smooth step. The details determine how quickly the plasma becomes well mixed. Reheating sets the initial temperature for the standard hot Big Bang evolution. It controls which particles are produced and how entropy is generated, and it can influence later relic abundances through the maximum temperature achieved. Even if inflation solves monopole overproduction by dilution, reheating must also avoid recreating unwanted relics at too high a temperature. The handoff must be energetic, but not reckless. The details of reheating are uncertain because they depend on how the inflaton couples to other fields. Different couplings lead to different thermal histories, different particle spectra, and potentially different imprints on observables like gravitational waves at smaller scales. In some models, reheating is quick and efficient. In others, it is prolonged and complex. The universe's earliest chemistry depends on couplings we have not identified. Yet the existence of some reheating-like process is required. Without it, inflation would leave an empty, cold universe with no plasma to make the CMB, no matter to form atoms, and no radiation bath to carry the acoustic signatures we observe. The universe we see demands that inflation, if it happened, handed off its energy to ordinary degrees of freedom. The prologue must connect to the story we already know. So inflation is not a replacement for the Big Bang model we tested earlier. It is a proposed prologue that sets up the hot phase, explaining why the initial conditions of the hot plasma were so special. The Big Bang becomes a chapter within a longer story, not the first page. The familiar timeline begins at reheating, but the preparation may have started earlier. At this point, inflation looks like a near-perfect tool. It explains uniformity, flatness, and the origin of fluctuations in one framework. And it does so with a mechanism that can be written in a compact set of equations. Yet the same mechanism that makes inflation powerful also opens doors that are difficult to close. A theory that stretches space so effectively may also stretch our notion of what counts as a prediction. Then the framework opens onto a more unsettling possibility. In many models, inflation is not a one-time event that ends everywhere, because quantum fluctuations can keep parts of the universe in the inflating state. The visuals widen again, our region ending inflation like a bubble forming in boiling water, while the surrounding medium keeps expanding. The end becomes local, not global. Quantum fluctuations can push the inflaton uphill in some regions, while it rolls downhill in others. Regions that stay high keep inflating, and because the expansion is so rapid, those regions can grow enormous even if they begin as rare patches. The stochastic nature of the field's evolution becomes a cosmic branching process. A small upward kick can matter more than a long classical roll. Because inflating regions expand so quickly, they can dominate volume even if they are rare. Inflation becomes eternal in a statistical sense, meaning it never ends everywhere at once, even though it ends locally in many places. The universe, on the largest scales, becomes a mosaic of endings and continuations. It is a picture of perpetual production, with pockets like ours forming again and again. In this picture, our observable universe is one bubble or pocket where inflation ended. Other pockets could have different low-energy physics, depending on how fields settle into minima of their potentials and how symmetries break. The implication is not merely many galaxies, but many regions with potentially different effective laws. The camera drifts across a foam of bubbles, each one a separate cosmic history. This is the multiverse-like implication of eternal inflation. It is not a separate add-on, but a consequence of certain inflationary dynamics, especially when the potential allows long-lived inflating regions. The idea is controversial partly because it strains the usual relationship between theory and observation. If most of the universe is forever out of view, what does it mean to claim we have explained it? Eternal inflation raises a new technical problem called the measure problem. If inflation produces infinitely many regions, probabilities become ambiguous, because counting outcomes depends on how you regulate an infinity. Different ways of regulating infinities can yield different predictions, so the theory risks losing explanatory power if it cannot define testable probabilities. Even the word likely becomes a moving target. There are also questions about falsifiability and selection effects. If every outcome happens somewhere, what does it mean to explain our specific outcome, rather than merely locating it within a vast ensemble? The worry is not philosophical decoration. It affects how we interpret predictions and how we connect parameters to observations. Are we learning deep laws or merely describing our address? Some physicists see eternal inflation as a warning that we are extrapolating too far. Others see it as a clue about how fundamental theory populates possibilities, perhaps reflecting a complex landscape of vacua in high-energy physics. Either way, the mood shifts from clean solution to open-ended frontier. The prologue becomes a labyrinth, and we are not sure which corridor leads to our page. Either way, the central mystery returns in a new form. Inflation may explain the hot Big Bang's initial conditions, but it may also demand its own origin, and it may do so in a setting where typical becomes hard to define. The more inflation explains, the more it asks us to clarify what counts as an explanation. We are forced to ask whether explanation means mechanism or something closer to inevitability. What is the vacuum that powered inflation, and why did it exist? If vacuum energy can drive a universe, then vacuum is not nothing, and the word empty becomes misleading. The inflationary vacuum is a physical state with energy, fields, and quantum fluctuations, and those ingredients can have measurable consequences. The silence of empty space begins to look like a kind of stored tension. The word nothing becomes slippery here. The inflationary vacuum is not a void, but a structured quantum state, defined by fields even when no particles are present. In that sense, the vacuum is a stage with tension in it, energy that can curve space-time and seed fluctuations. When we say empty, we may only mean empty of particles, not empty of physics. Inflation turns that physical vacuum into structure through stretching and freezing. It converts microscopic uncertainty into macroscopic pattern, and then hands those patterns to the hot plasma as initial ripples. The universe's later complexity is therefore linked to the unavoidable restlessness of quantum fields. The largest patterns in nature may have begun as unavoidable jitter. This is the chapter's culminating idea, and it is both elegant and eerie. The universe's largest structures may be the fossilized imprint of quantum noise, preserved across billions of years of expansion. When we map galaxies, we may be mapping an ancient quantum random number generator. The randomness is disciplined, shaped by simple rules, yet it remains randomness. Galaxies would then be the long-term consequence of fluctuations that had no classical cause. They would be the amplified residue of a vacuum state, shaped by gravity into filaments, nodes, and voids. The visuals here are a slow morph, from a faint speckle in the CMB to the luminous cosmic web. The same pattern repeats across scales, like a theme returning in a symphony. Yet even this does not settle the deepest question. Why was there an inflating state at all, and why did it begin rather than not, if the vacuum is itself a physical thing that must be accounted for? Inflation moves the boundary of ignorance earlier, and it changes what we mean by a beginning. It replaces a singular start with a dynamical prelude, but the first note is still mysterious. It suggests the Big Bang was not the first event, but a transition. That transition is reheating, when accelerated expansion gives way to a hot, particle-filled universe, and the arrow of thermal history begins its familiar descent. The Big Bang becomes a change of phase, not a creation from nothing. The beginning becomes a handoff, and handoffs always imply something on both sides. So we end with a pivot rather than a conclusion. Inflation is a leading framework, but its mechanism and initial conditions remain uncertain, and the most important unknown may be the identity of the inflaton itself. The data favor its broad predictions, yet the underlying physics is still unidentified. We have a compelling outline, but the ink is not fully legible. The prologue fits the evidence, but the author is unknown. We can read the traces, in the CMB spectrum, in the near-flat geometry, in the absence of relics, and infer a plausible opening act. But we do not yet know which fundamental theory wrote that act, or whether another script could produce the same scenes. In science, fitting the plot is not the same as identifying the writer. And the cause question remains, sharpened by progress. If inflation is one possible prologue, there are others where the universe avoids a singular start, and where the earliest gap is crossed by different dynamics. If inflation is not the only bridge across the earliest gap, we must compare it to rival bridges. The comparison is not a threat to inflation, but a demand for clarity. Some scenarios replace the beginning with a rebound from a prior phase. They keep the mystery but change its shape, trading a sudden fast forward for a cosmic return. Next, we turn to those alternatives, where the universe may have bounced instead of begun. The mystery shifts from fast forward to return. We ended with inflation as a powerful prologue and an unfinished origin story. Now we test other doorways that claim the Big Bang was not a first moment. The corridor looks the same at first, lit by the same equations, the same symmetries, and the same hard-won confidence. We run the mathematics backward. The scale factor shrinks, density rises, and temperature climbs toward regimes no laboratory can reproduce. Galaxies dissolve into plasma. Atoms cannot hold, and even nuclei become a hot, interacting soup of quarks and gluons. At still earlier times, electroweak physics may restore symmetries we now see broken, and familiar particles blur into unified fields. The numbers keep tightening until classical spacetime begins to strain under its own assumptions. The familiar warning light returns, an alarm built into general relativity when curvature grows without bound. In Einstein's theory, the past-directed trajectories of matter and light can converge so strongly that the equations stop giving meaningful predictions. General relativity predicts a singularity, then stops speaking in meaningful numbers, as if the map ends at a cliff. It is not merely that density becomes large, it is that the geometric description loses the ability to extend histories smoothly. The singularity is not a place we have observed, and it is not an object floating in space. It is a boundary where extrapolation breaks, where geodesics cannot be extended, and where quantum gravity should matter. If the boundary is real, the universe begins there, full stop, with no earlier chapter. If the boundary is an artifact of using classical equations beyond their domain, something lies on the other side. The question becomes sharply practical. Which assumptions fail first, and what replaces them? Alternative models share one motive, and it is almost modest in wording. Replace the classical singularity with a prior phase that stays finite, so the theory does not demand an actual infinity. They do not remove mystery, they relocate it, and they charge a price in new ingredients. The corridor does not open into daylight, only into different kinds of darkness. Each darkness has its own mathematics, and each mathematics makes its own promises. We treat each model like a doorway at the end of the same corridor, each with its own handle and its own lock. One doorway opens onto a bounce, where collapse reverses into expansion. Another opens onto cycles, where the universe repeats, or at least rehearses, the same drama across epochs. A third opens onto a quantum beginning where time is not fundamental, and where before may be the wrong question. The doors look similar from a distance, yet their hinges are built from very different physics. Start with the simplest reversal, because it is the easiest to picture. The universe expands today, so imagine it once contracted, with distances shrinking rather than stretching. In a contracting phase, the scale factor falls, densities rise, and the arrow of time becomes a question rather than a given. What counts as earlier when the universe is compressing toward extreme curvature? Even the meaning of horizon changes, because causal contact can behave differently in a long contraction. A big bounce cosmology says, contraction precedes expansion, and the Big Bang becomes a turning point rather than a creation event. The central claim is dynamical, not rhetorical, and it can be stated in the language of equations. Gravity changes effectively at extreme density, so collapse halts and reverses, as if attraction is replaced by repulsion when space-time becomes too tightly packed. The bounce is not a denial of the hot Big Bang, it is a rewrite of the first page. In classical general relativity, collapse tends to accelerate into a singularity, because energy density focuses geodesics and amplifies curvature. To get a bounce, something must violate the conditions that make singularities inevitable, at least for a time. That something can be exotic matter with unusual pressure, modified gravity that changes Einstein's equations, or quantum geometry itself. Each option is a different bet about where classical reasoning fails. Loop quantum cosmology offers a concrete example of the last option, and it is valuable because it is calculational rather than purely metaphorical. It applies ideas from loop quantum gravity to a highly symmetric cosmological setting, where the universe is treated as homogeneous and isotropic to first approximation. Space-time geometry becomes quantized, and the classical Friedmann equations gain effective corrections that encode discrete geometry. The model is simplified, yet it is precise enough to make sharp statements about the bounce. In this approach, areas and volumes come in quanta, and the smooth continuum becomes an approximation that fails near the Planck regime. The correction acts like repulsion when density approaches a critical value near the Planck scale, roughly where quantum gravitational effects can't be ignored. The energy density stops growing, the Hubble parameter crosses through zero, and expansion begins. The bounce is not a miracle. It is the result of new terms that dominate only at extreme curvature. In many treatments, the effective equation resembles a classical universe with an additional negative density contribution, a bookkeeping device for quantum geometry. Visually, the scene is not an explosion from a point, but a cosmic breath. The universe contracts like a slow exhale, the background glow intensifies, and then, at a density threshold, the contraction stalls. The geometry does not tear, it rebounds, and the same space-time that was shrinking begins to stretch again. If we could watch it as a film, the moment of reversal would look almost gentle, like a tide turning under a hidden moon. This changes what the Big Bang means without erasing the hot, dense story we already know. The hot state is still real, and nucleosynthesis and recombination still happen later in the timeline. But the earliest moment becomes a bridge between two classical regimes, separated by a quantum phase where the usual geometry is not continuous. The bang is a transition in the behavior of gravity, not a first tick of a universal clock. The familiar thermal history remains, but its origin becomes a dynamical pivot. A bounce model must answer a hard inheritance question, and it cannot be avoided by clever language. What passes through the bounce, and what does not? Do perturbations survive? Do they change phase? And do they keep memory of a pre-bounce universe? A universe that bounces must decide what it remembers. That memory is not sentimental. It is encoded in correlation functions we can, in principle, measure. In practice, this means tracking fluctuations in density and curvature through a region where classical spacetime is replaced by effective quantum dynamics. Small ripples in the pre-bounce contraction could become the seeds of galaxies after the bounce, but only if they remain well-behaved. If information survives, the past might be observable in principle, encoded in correlations we can measure. If information is erased, the bounce becomes a reset, and the prior phase becomes empirically unreachable. The distinction is subtle, because some information can survive while other details are washed away. The model's promise depends on whether it leaves a trace that cannot be mimicked by inflation. If every surviving signature can be tuned away, the bounce becomes a philosophical preference rather than a scientific alternative. Yet if certain patterns are robust, specific oscillations, phase relations, or a characteristic cutoff, then the prehistory becomes more than a story. Robustness matters because cosmology is a game of small signals, and fragile predictions rarely survive contact with data. Bounces also face a stability problem that sounds technical but has a simple image. In contraction, anisotropies and inhomogeneities can grow rapidly, like a mixture that curdles as it is squeezed. Shear terms scale strongly during contraction, and small deviations from perfect uniformity can amplify into chaos. Without a smoothing mechanism, contraction tends to produce a turbulent approach to the bounce, not a clean handoff. The universe can arrive at the turning point already distorted, and distorted initial conditions are hard to redeem. Some bounce scenarios add matter fields with special equations of state to control that growth, making the contracting universe behave like a stiff fluid. Others rely on modified gravity terms that change how shear evolves, damping anisotropies before they dominate. Either way, the price is explicit. You gain a prehistory, but you must keep it from becoming a mess. The mathematics can do it, but it must do it without breaking other parts of physics. There is also a practical concern that hides inside the mathematics. Any mechanism that violates classical energy conditions risks instabilities, such as ghosts or runaway modes, unless carefully constructed. The bounce must be gentle enough to preserve predictability, yet strong enough to prevent a singularity. That balance is delicate, and it is part of why the corridor remains dim. A model can avoid infinity and still lose control of causality or unitarity, and that would be a different kind of failure. Now open the second doorway, where the story is not a single reversal, but a repeated rhythm. Cyclic and ekpyrotic models do not merely bounce once. They propose repeated phases, or a long pre-Big Bang contraction that prepares the universe for what follows. The Big Bang becomes one beat in a larger cosmic cadence. The appeal is immediate. If there is no first beat, there is no need for a first cause. The ekpyrotic idea is a specific kind of contraction, and it is designed to solve a familiar problem in a different way. It is slow, ultra-stiff, and smoothing, with an equation of state far greater than that of ordinary matter or radiation. In simple terms, pressure is enormous compared to energy density, and that changes which components dominate the dynamics. The contraction can last long enough to act like a cosmic preparation phase, rather than a brief collapse. This is the key trick, and it is more than a slogan. In ekpyrotic contraction, the energy density in the ekpyrotic field grows faster than curvature and anisotropy as contraction proceeds. That dominance makes the contracting universe approach a homogeneous, flat attractor solution. The universe can become flatter and more uniform while shrinking, not while inflating. The attractor behavior is the engine of the proposal, because it makes smoothing generic rather than finely tuned. The horizon and flatness problems are addressed without a standard inflationary fast-forward. Instead of stretching a tiny region to cosmic size, ekpyrosis uses a long, controlled contraction to align conditions across space. The smoothing happens before the hot phase, through a different dynamical attractor, and the universe arrives at the bounce already prepared. In this view, the Big Bang is not the moment order appears. It is the moment a prepared state is reheated. The visuals here are counterintuitive because contraction feels like the opposite of order. Imagine a vast, dim cosmos slowly compressing, yet becoming calmer as it tightens, like a lens focusing light into a cleaner beam. The background becomes more uniform, gradients fade, and the geometry approaches a simple form, even as scales shrink. dusty irregularities that would dominate in ordinary contraction are suppressed, and the approach to the bounce becomes almost serene. In some versions, the story is higher dimensional, and the language becomes more geometric. Our observable universe is a brain in a larger space, a three-dimensional surface embedded in a higher dimensional bulk. The Big Bang corresponds to a brain collision or a brain interaction, converting kinetic energy in extra dimensions into heat and particles on the brain. The collision is a metaphor with equations behind it, and the equations live in a broader gravitational framework. The brain picture is not required for every cyclic model, but it captures the tone of the proposal. The Big Bang becomes a contact event, not a creation event, and the cause is motion in a higher dimensional setup. The cost is extra structure we cannot directly see, and the reward is a mechanism that can, in principle, reset conditions. It also reframes what space means, because our three dimensions become a surface with an environment. Cyclic models then extend the idea into a long narrative. Expansion, cooling, and structure formation occur, and stars and galaxies form as they do in the standard picture. Then a mechanism triggers a turnaround, leading back to contraction, then another bounce, then another hot phase. The universe becomes a repeating sequence of eras, each one leaving a faint imprint on the next. Even the word age becomes ambiguous, because local histories can repeat while global time marches on. Historically, the appeal of cycles is old, and it predates modern cosmology by millennia. Philosophers imagined eternal recurrence because it avoided a first cause, and it made time feel symmetrical. Modern cyclic models are not those ancient cycles, because they must respect thermodynamics and fit precision data. Still, the emotional pull is similar. A universe without a first page. When 20th century cosmology turned the Big Bang into a scientific framework, cycles returned as a disciplined counter-proposal. This is where the tension sharpens into a technical constraint. A cyclic universe must confront entropy, because entropy is the accountant that never forgets. In ordinary thermodynamics, entropy increases, and cycles should accumulate disorder. If entropy grows each cycle, later cycles become longer and larger, and the past becomes effectively finite anyway. The universe may look cyclic locally, while the global story still has a beginning hidden in the bookkeeping. This is the entropy problem for cyclic cosmology, and it is not a minor bookkeeping detail. How do you avoid a heat death that builds up across cycles? How do you prevent each cycle from carrying more relic photons, more black holes, and more irreversible debris? A truly cyclic universe must either export entropy or redefine what a cycle means. The challenge is not just conceptual, it is quantitative, because entropy can be estimated and constrained. Proposed mechanisms exist, but none is universally accepted, and each comes with its own assumptions. Some models dilute entropy by expanding the universe enormously between cycles, so each new cycle begins in a nearly empty state. The entropy is still there, but it is spread thin, like ink diluted in a growing ocean. Some invoke entropy being dumped into extra dimensions, or into regions that become causally disconnected. The proposals are imaginative, yet they must be consistent with gravity, quantum field theory, and the observed cosmic inventory. Other proposals modify what counts as a cycle, separating a local observable patch from a global space-time that grows. The patch can reset while the whole does not, so an observer experiences repetition without requiring strict global periodicity. These are clever moves, but they reveal the price. Cycles demand accounting across epochs, and the accounting is hard. The deeper question lingers. Are we describing a truly repeating universe, or a universe that only appears repetitive from inside? Even if entropy can be managed, perturbations must be managed too, because the sky is not negotiable. A cyclic model must generate the observed spectrum of primordial fluctuations. It must match near-scale invariance, near Gaussianity, and the phase coherence seen in the CMB acoustic peaks. Those peaks are a precise pattern, like a chord that must be played in tune. Any alternative must reproduce not only the notes, but their timing. Ekpyrotic models can generate nearly scale-invariant perturbations, but the route is often more intricate than in simple inflation. Many versions require multiple fields, where one field drives smoothing and another carries fluctuations. Then a conversion mechanism transfers entropy perturbations into curvature perturbations at or near the bounce. The details matter because the statistics can differ from inflation. A small change in the conversion can shift the predicted non-Gaussianity, and that shift is observable in principle. Non-Gaussianity can be larger, and its shape can be distinctive, depending on interactions and the conversion process. Inflation often produces very small non-Gaussianity in its simplest forms, while ekpyrotic scenarios can naturally generate higher-order correlations. That difference becomes a potential fingerprint if observations can isolate it from late-time non-linearities. The universe's large-scale structure is not just a map of where matter went, it is a record of how fluctuations were born. The tensor spectrum can be very different as well, and tensors are the cleanest messengers because they interact weakly. Inflation often predicts a spectrum of primordial gravitational waves tied to its energy scale, with power on large scales that can imprint B-mode polarization. Ekpyrotic contraction typically predicts a strongly blue tensor spectrum, making large-scale primordial gravitational waves extremely small. That contrast is not a minor detail, because it changes what future detectors should expect to see. So the gravitational wave background becomes a discriminator, and it is one of the corridor's bright signposts. A detection of large-scale primordial B-modes would favor many inflationary models and strain many ekpyrotic ones. A continued non-detection, combined with other signatures, keeps the corridor open to contraction-based alternatives. The absence of a signal is not proof, but it is pressure. In cosmology, pressure accumulates slowly as upper limits tighten and parameter space shrinks. But the corridor is not only about bounces and cycles, because mathematics also tries to close the door. The singularity theorems of Hawking and Penrose show that under certain conditions, singularities are unavoidable. They were developed in the 1960s and 1970s, when relativity matured into a rigorous global theory of spacetime. In a sense, they formalized the intuition that gravity, left unchecked, creates edges. They also changed cosmology's tone because they replaced hand-waving with theorems. The theorems are not about the Big Bang as a specific event, and they do not claim that a singularity is a physical object. They are about geodesic incompleteness, the failure of spacetime to extend smoothly along the paths that particles and light would follow. The conclusion is that the classical description cannot be complete. Something ends, and the theory does not tell you what lies beyond. The theorems are like a sign that says, past this point, the coordinates stop meaning what you think. They rely on assumptions, and those assumptions are where alternative models look for room. Spacetime is classical and smooth. Energy conditions hold, and gravity focuses geodesics rather than defocusing them. These conditions are plausible at low energy, where matter behaves normally and quantum effects average out. Near the Planck scale, they may fail. The doorways we are testing are, in a sense, attempts to change the premises without breaking the rest of physics. Quantum fields can violate classical energy conditions in controlled ways. Even in ordinary quantum theory, negative energy densities can appear locally, constrained by quantum inequalities, and vacuum fluctuations can produce stress energy that does not behave like classical matter. Quantum geometry may not be a smooth manifold at all, and the notion of a point may lose operational meaning. The loophole is not a loophole of laziness. It is a loophole created by quantum reality. This is the loophole space, and it is both promising and unsettling. If energy conditions are violated, focusing can be avoided, and a bounce can occur without a singularity. If space-time is not classical, the theorem's premises are not satisfied, and the conclusion does not apply. If causality itself becomes fuzzy, the notion of a classical geodesic may be the wrong tool. The corridor widens here, yet the footing becomes uncertain. Inflation already hints at this tension, because a vacuum-like state with negative pressure changes the focusing behavior of geodesics. Yet even inflation, in many formulations, does not automatically remove the need for an initial boundary. It can push the boundary back, and it can make it less singular, but it often does not erase it. The universe may inflate and still require an earlier rule that selects the inflating patch. There is a result that keeps the unease alive, and it is often summarized in one unsettling phrase. Under broad conditions, inflationary spacetimes can be passed incomplete, meaning they cannot be extended arbitrarily far backward along geodesics. That does not prove a singularity, and it does not specify what the boundary is. It suggests a beginning of some kind, or at least a boundary where the description changes. Even the most successful early universe mechanism can inherit the same question it tried to soften. So we face a layered problem, like walls built inside the corridor. Classical theorems point toward boundaries, and they do so with mathematical force. Quantum corrections offer loopholes, but they are hard to compute and easy to overpromise. Alternative cosmologies exploit those loopholes, but they must still produce our observed universe, not merely a void and infinity. The corridor is a place where rigor and imagination argue in the same language. Now open the third doorway, where the premise changes more radically. Quantum cosmology does not start with a classical spacetime that evolves. It starts with a quantum description of the universe as a whole, where geometry is part of the wave function. Instead of quantizing fields on spacetime, it tries to quantize spacetime itself. The move is bold because it removes the stage as well as the actors. The canonical symbol here is the Wheeler-DeWitt equation, which emerged in the late 1960s as a formal attempt to apply canonical quantization to general relativity. It is often described as a Schrödinger equation for the universe, but with a crucial twist. There is no external time parameter in the usual sense, because the universe has no outside clock. The equation is a constraint, and the constraint is the story. In this framework, the universe is described by a wave function over configurations of geometry and matter fields. The wave function assigns amplitudes to different possible 3 geometries and field values, like a probability amplitude spread across possible shapes of space. Classical spacetime emerges only in regimes where the wave function is sharply peaked around a semi-classical history. In plain language, the universe looks classical when quantum uncertainty in geometry becomes small. The emergence is not automatic. It depends on decoherence, coarse graining, and which histories dominate. This is not a poetic move, and it is not merely a metaphor for ignorance. It is a technical attempt to quantize gravity in a constrained system, where the Hamiltonian is not a generator of time evolution in the usual way. The constraint replaces ordinary evolution, and the absence of time becomes a feature, not a bug. The famous problem of time is not a footnote, it is the center of the room. If time is emergent, then beginnings are not events in time, but conditions on histories. If time is not fundamental, the cause question changes shape, because causes live inside time. A quantum cosmological boundary condition is not a cause in the ordinary sense. It is a rule that selects which histories have non-zero amplitude. The universe does not begin because something pushes it. It begins because certain histories are allowed. That may sound abstract, yet it is a precise shift in what explanation means. Two famous proposals offer competing boundary conditions, and they are often presented as rival answers to the same question. Hartley and Hawking propose the no-boundary idea, built from a path-integral approach to quantum gravity. Vilenkin proposes a tunneling idea, framed as a quantum transition into an expanding universe. Both are attempts to replace a singular start with a quantum rule. Both also raise the same uncomfortable issue. What exactly is being summed over? In the no-boundary proposal, the universe has no initial boundary in the classical sense, and the earliest regime is described by compact geometries. The path integral is dominated by smooth, closed configurations, so the beginning is like a rounding off rather than an edge. The universe is finite but unbounded, like a surface without an edge. The geometry closes on itself, and the concept of before loses traction. The earliest, time, behaves more like a coordinate label than a ticking clock. In this picture, asking what happened before becomes like asking what is south of the South Pole. The coordinate ends, but the geometry is regular, and the question misfires. The beginning is replaced by a smooth transition where the distinction between time and space can blur. What we call time can behave like a spatial dimension in the earliest regime. Visually, the universe's first frames would look like a smooth cap, not a sharp corner. Vilenkin's tunneling proposal answers the same question differently, and it leans into the language of quantum transitions. It treats the universe as a quantum system that can tunnel into existence from a state with no classical spacetime. The amplitude favors certain initial conditions, and the universe emerges as an expanding branch. The first classical moment is not a point of infinite density, but a nucleation of geometry. The image is not a blast, but a bubble of spacetime becoming real enough to host clocks. Both proposals are attempts to answer a version of the oldest question, and they do so with technical tools rather than metaphysical declarations. Why is there something rather than nothing? They do not answer it in the language of everyday philosophy. They answer it with boundary conditions and quantum amplitudes, and with a calculus of which histories are permitted. The question remains ancient, yet the proposed answers are written in modern symbols. The word nothing must be handled carefully here, because it is easy to smuggle in confusion. In tunneling discussions, nothing often means no classical space-time, not the absence of laws or possibilities. It can mean no geometry, no time coordinate, and no classical fields defined on a background. It is a technical nothing, defined by what the classical description lacks. The word is familiar, but the definition is specialized. That is not a philosophical void, and it is not absolute non-existence. It is a state where the classical concept of space-time does not apply, but where a quantum description still assigns amplitudes. The vacuum is not necessarily empty. It is a structured quantum state, and structure can be unstable. Even empty space can have fluctuations, correlations, and energy scales. If the vacuum can decay, then nothing can be a metastable arrangement rather than a final absence. So tunneling from nothing is not a claim that absolute non-existence produced existence. It is a claim that classical spacetime can emerge as a quantum event, like a transition between regimes of description. The universe begins as a quantum possibility, then becomes a classical history as decoherence and semi-classical behavior take hold. The event is the birth of a classical narrative. The deeper puzzle is whether that narrative is unique or one branch among many allowed histories. This is where the tone becomes deliberately mysterious, because the subject is not an explosion, but a change in what counts as an event. We are not watching matter fly outward from a center. We are watching the rules that define time, geometry, and measurement come into focus. The Big Bang becomes less like a first frame and more like a boundary between quantum and classical storytelling. The camera, if it existed, would be filming the emergence of the camera itself. Yet quantum cosmology also pays a price. And it is not merely aesthetic. The mathematics is hard, the measure over histories is ambiguous, and the interpretation of probability is subtle when there is only one universe to talk about. Even defining what counts as an observation becomes part of the model. When the observer is inside the system, probability becomes a delicate word. The theory must explain not only what happens, but what it means to say that something happens. There is also the practical issue of approximation, because the full space of geometries is vast. Many calculations rely on mini-superspace models, where only a few degrees of freedom are kept, such as the scale factor and a homogeneous field. That makes the problem tractable, but it raises a question: which features survive when the approximation is relaxed? The corridor offers a doorway, but the room beyond is still under construction. A boundary condition that works in a simplified model may behave differently in the full theory. And the models must still meet the sky, because cosmology is not satisfied by internal consistency alone. A good origin story must leave a fingerprint, because we do not get to rerun the universe in a laboratory. The corridor ends at the same locked door. Can we distinguish a true beginning from a bounce using observations? If we cannot, we are left with multiple stories that fit the same data. The universe may permit several narratives, while giving us only one set of measurements. This is the chapter's peak tension, and it is more than a rhetorical flourish. A bounce can mimic inflation's predictions, and inflation can mimic some bounce signatures, especially when parameters are flexible. A quantum beginning can be tuned to resemble either, depending on how semi-classical histories are selected. The universe may be generous with beauty and stingy with clues. That stinginess forces us to ask which predictions are unavoidable and which are adjustable. So we ask for discriminators, and we accept that they will be statistical rather than absolute. Primordial gravitational waves are one because they propagate almost freely once produced. Their spectrum, tilt, and amplitude can differ between inflationary expansion and ekpyrotic contraction, and between different bounce mechanisms. The polarization patterns in the CMB become a fossil record of early time dynamics. If we ever read that fossil cleanly, we will be reading the universe's earliest stress and strain. Non-Gaussianity is another, and it is a way of asking whether the primordial fluctuations were simple or interactive. Multi-field dynamics, conversion mechanisms, or non-trivial interactions can leave higher-order correlations in the CMB and in large-scale structure. The shape of the bispectrum can point to specific physics, not just to a generic early-time disturbance. It is like comparing not just the loudness of a note, but its timbre. A universe born from a single smooth field sounds different from a universe born from coupled fields exchanging fluctuations. Relic features in the power spectrum are another possible clue, and they are especially tempting because they can look like scars. A bounce or a transition can imprint oscillations, cutoffs, or localized departures from a smooth, nearly scale-invariant spectrum. These features can survive as subtle anomalies in CMB multipoles or in galaxy clustering statistics. The challenge is separating a primordial feature from a statistical fluke or a foreground artifact. The sky is a single sample, and cosmic variance is the price of having only one universe to observe. Cosmic topology is another possible hint, and it is one of the most visual ideas in the corridor. If space has a non-trivial global shape, light can wrap around, producing matched circles or repeated patterns in the CMB. Topology is difficult to measure, and the limits are strong, but it remains a doorway to prehistory. A finite but unbounded space would change what elsewhere means. It would also change what infinite means, replacing it with a geometry that closes without an edge. There are also signatures in relic particle backgrounds, which are quieter than light but can carry older news. A pre-Big Bang phase might produce gravitational wave backgrounds at frequencies far from CMB scales, accessible to pulsar timing arrays or future interferometers. It might also produce relic defects or isocurvature modes, which are constrained but not fully excluded. Each constraint is a narrowing of the corridor, not a closure. Each new survey is another pass of the flashlight along the walls. Every proposed fingerprint faces the same problem, and it is the practical reality of cosmology. The early universe is a noisy messenger, and the message arrives through layers of later physics. Late-time astrophysics, foregrounds, and parameter degeneracies can imitate or hide the signal. Even our instruments add their own patterns, and those patterns must be modeled and subtracted. The cleanest early universe clue can be blurred by dust in our own galaxy. And that is a humbling fact. So the strategy becomes statistical and comparative, as it must in a science with one sky. We do not ask for a single smoking gun, because the universe rarely provides one. We ask for a consistent pattern across probes, where one model fits naturally and rivals must contort. The best theory is not the one that can fit anything, but the one that fits without strain. Over time, the corridor narrows, not by argument alone, but by accumulated evidence. This is why the corridor metaphor matters, and why it keeps returning. Each doorway offers a way around the singularity, but each demands new commitments. A bounce demands modified gravity or exotic matter and a stable passage through contraction. A cyclic model demands entropy control and a robust perturbation mechanism. A quantum beginning demands a boundary condition and an interpretation of probability without external time. The doors are not free, they are paid for with assumptions. The singularity theorems remain the stern sign at the corridor's end, and they are not easily ignored. They say classical spacetime plus reasonable energy conditions leads to incompleteness. And incompleteness is a kind of beginning. The loopholes say those conditions may fail where we most need them, and where we least know how to calculate. The argument becomes a contest between rigor and unknown physics. We can feel the shape of the problem even when we cannot yet solve it. So we are left with a disciplined uncertainty, which is not the same as confusion. The Big Bang could be a beginning, with no meaningful earlier time. It could be a bounce, with a prehistory that left faint traces. It could be a quantum emergence where the word before is a category error. The corridor does not tell us which door is true, but it tells us what each door would require. The difference is not only philosophical, and it is not only a matter of taste. It is encoded in what we should look for in the sky and in how we interpret what we find. If the universe bounced, it may carry a faint memory of a previous phase, hidden in correlations and spectra. If it began quantum mechanically, it may carry a signature of the boundary condition that selected its history. The question becomes almost personal, in a scientific way. What kind of evidence would change our mind? We return to the central question with sharper edges, because the corridor has taught us what is at stake. If the Big Bang marks the origin of our observable universe, what caused it, and what does nothing mean in modern physics? In these models, cause can become a transition rule, and nothing can become a physical state with quantum structure. The words stay familiar, but their meanings shift. The deeper we go, the more language becomes part of the experiment. and we end on a pivot that sets the next chapter's deeper riddle. Even if we find a model that removes the singularity, we still face a deeper riddle. What is a vacuum? What is nothing? And can nothing be unstable? That question is not a retreat into abstraction, and it is not an escape into wordplay. It is the next experimental frontier, because vacuum energy, quantum fluctuations, and metastable states can leave measurable traces. The corridor continues, and the next door is labeled not beginning, but vacuum. We ended at the edge of beginnings, where singularities and bounces still leave a question hanging in the dark. Now we interrogate the word nothing, because modern physics refuses to let it stay simple. The camera can linger on a black sky that looks vacant, then let equations and faint grids seep into it. In everyday language, empty space is absence, a quiet container waiting to be filled with matter, light, or sound. In quantum field theory, empty space is a state of fields, and fields are the primary objects, more fundamental than the particles we count. What looks like a void is, in the theory, a specific configuration with rules, correlations, and a definable energy. A field is not a metaphor, and it is not merely a mathematical trick for convenience. It is a physical quantity assigned to every point in space-time, like an invisible weather map whose values can ripple and change. Even when no particle is detected, the field is still there, defined and ready to be disturbed. In experiments, we never turn off the electromagnetic field. We only prepare it in a particular quantum state. Particles are excitations, like notes played on instruments that never leave the stage. The electron is not a tiny bead moving through emptiness, but a localized pattern in the electron field. A photon is not a pellet of light, but a quantum of excitation in the electromagnetic field. The particle picture is useful, yet it is a shorthand for how fields exchange energy in discrete amounts. Even with no particles present, the instruments remain, and their lowest energy state still has activity. The vacuum is not a substance, yet it has measurable consequences, and those consequences are not philosophical decoration. It is defined by expectation values, correlations, and the rules that constrain fluctuations. When we say vacuum, we mean a state that tells every detector what statistics to expect. In practice, physicists specify a vacuum by how it responds to operators, how it correlates measurements at separated points, and which symmetries it respects. The vacuum is a reference state, but it is also a dynamical one, because the fields never fully stop moving. The calm we imagine is an approximation, a coarse-grained picture drawn over restless mathematics. Even the definition of lowest energy depends on the space-time and the observer's notion of time. The uncertainty principle blocks perfect stillness in the ground state. Conjugate quantities cannot both be sharp, so the vacuum retains irreducible jitter even when temperature is zero and no classical motion remains. The simplest example is a harmonic oscillator, whose lowest energy state still has non-zero variance in position and momentum. That variance is not a mistake. It is the minimal blur required by the commutator. Quantum fields are like an infinite collection of oscillators, one for every wavelength and direction. Each mode contributes a minimum amount of fluctuation, and the vacuum is the state where those modes are as quiet as the rules allow. Quiet here is a technical word, meaning minimal energy consistent with commutation relations. If we visualize it, the darkness should shimmer with tiny, symmetric ripples that never quite freeze. Those fluctuations are not free energy that can be harvested at will. They are constrained by conservation laws, by locality, and by the structure of the quantum state, so they do not behave like a battery waiting to be drained. If you try to extract work, you must couple to the field, and that coupling changes the state you call vacuum. The vacuum can be disturbed, but the disturbance is part of the accounting, not a loophole. Still, the vacuum can push on the universe through gravity, because in general relativity, energy and pressure shape space-time. The vacuum becomes part of the source term, not a philosophical afterthought, and that changes the tone of the origin question. We are no longer asking what filled emptiness, but what state emptiness itself occupied. A blank screen becomes a weighted screen, subtle, but cosmologically decisive. This is where the cause question changes character. Instead of a shove from outside, the beginning can be a change of state inside the rules, like a system reorganizing when parameters drift. The trigger becomes internal, encoded in the landscape of allowed configurations. The universe begins to resemble a metastable material poised near a threshold, except the material is the vacuum itself. Quantum fields come with potentials, and potentials come with multiple minima. A vacuum is not just emptiness, it is which minimum the fields occupy, and that choice can determine what kinds of particles even exist. The potential is a kind of energy topography, with valleys, ridges, and false basins that can trap a system. In visuals, the landscape should look like a dim terrain map, smooth in places, jagged where instabilities hide. When the universe cools, the preferred minimum can change, because temperature alters the effective potential. Symmetries that were restored at high temperature can break, and the vacuum can reorganize, selecting one valley among many. In plain language, the rules stay the same, but the favored arrangement shifts. Thermal corrections come from the surrounding plasma, which pushes back on the field's preferred value. Phase transitions are the language for that reorganization. They are familiar in matter, yet in cosmology, the medium is the vacuum itself, and the stakes are larger than ice melting. In a laboratory, we watch water pick a phase. In the early universe, fields pick a vacuum. The early cosmos is a furnace of interactions, where symmetry can be an emergent property of heat. In a thermal phase transition, a system releases latent heat as it changes phase. In the early universe, the analogy is energy released as fields roll or tunnel into a new vacuum, converting potential energy into motion, radiation, and particle production. The phrase reheating is literal in effect, even if the mechanism is quantum. The energy does not appear from nowhere. It is redistributed from the field's stored potential. That released energy can reheat the universe, populating particles and radiation from a previously dilute state. The hot Big Bang can be the aftermath of a vacuum transition, not the first act, and that reframes the beginning as an internal conversion. Instead of matter appearing from nowhere, energy stored in a field becomes the thermal bath. The scene can brighten from cold emptiness into a fog of glowing plasma, as if the vacuum itself combusts. Inflation already hinted at this logic because it used a vacuum-like equation of state. A nearly constant energy density with negative pressure drives accelerated expansion, stretching space so rapidly that initial irregularities are diluted. The vacuum in this phase behaves as if it resists being diluted by expansion. That resistance is not stubbornness. It is the property of a state whose energy density stays approximately constant as volume grows. The key parameter is W, the ratio of pressure to energy density. For vacuum energy, W is near -1, and that makes expansion speed up, because the Friedmann equations couple pressure as well as energy density to cosmic acceleration. This is one of the most counterintuitive facts in cosmology. Pressure can gravitate. In the equations, negative pressure effectively acts like a repulsive contribution to the expansion dynamics. This is not a force pushing matter outward through space. It is the metric evolving so that distances grow faster, even in regions with no particles, and even between points that are locally at rest. The expansion is not an explosion into emptiness, but a change in the ruler we use to measure separation. The visual cue is subtle. Galaxies do not fly through space, but the grid between them stretches. Inflation is the dramatic case, where vacuum-like energy dominated briefly and then ended in a conversion. Dark energy is the quiet case, where a similar behavior appears to dominate today, but at an astonishingly smaller density. The same mathematics describes both, and that resemblance is both elegant and suspicious. It invites a question that feels almost personal. Why does the vacuum return to the story when we least expect it? The same equation of state links the first instance to the present epoch. That link is unsettling, because it suggests vacuum physics is not a one-time trick, but a recurring theme in the universe's evolution. If the vacuum can drive expansion twice, what else can it do in between? Perhaps the emptiest thing we can name is also the most persistent actor we have ignored. If vacuum energy can accelerate expansion, then the vacuum is a dynamical actor. The question becomes which vacuum we are in and whether it is stable, because stability is not guaranteed by the word empty. A vacuum is a state, and states can be temporary. The universe may be calm only because it is, for now, sitting in a valley that has not yet revealed its exit. Early universe phase transitions are not optional in the standard model of particle physics. The electroweak symmetry breaks, and the Higgs field acquires a non-zero vacuum value, changing the behavior of the weak force. This is not a cosmetic change, because it reshapes the spectrum of particles. The universe's cooling is not just a drop in temperature, it is a sequence of reorganizations in what mass and force even mean. The Higgs vacuum expectation value gives masses to W and Z bosons and to fermions through couplings. Mass is not merely a property of particles, it is a property of the vacuum state, because the vacuum sets the background value the Higgs field takes. In everyday terms, the vacuum is part of what makes matter heavy. Without that background value, electrons would behave differently, and chemistry would not be chemistry. At high temperatures, the Higgs potential is modified by thermal corrections. The symmetric phase can be favored, and then later, the broken phase becomes preferred as the universe expands and cools. The potential effectively reshapes itself because the surrounding plasma contributes to the Higgs field's energy. The vacuum is not choosing in isolation. Its environment, the hot bath of particles, changes the shape of the choice. Whether that transition is first order or a smooth crossover depends on parameters. In the standard model with the observed Higgs mass, it appears to be a crossover, meaning there is no sharp latent heat release like boiling water. Yet even a crossover is a real reorganization, with consequences for particle interactions. The absence of a dramatic jump does not mean nothing happened. It means the change was continuous, like a slow turning of a dial. Even a crossover still marks a change in degrees of freedom and in effective masses. The vacuum reorganizes, and the plasma's behavior changes with it, altering reaction rates and the way energy flows among species. In the early universe, small changes in rates can cascade into large differences in relic abundances. A tiny shift in timing can decide what survives as the universe thins out. Other transitions could have occurred at higher energies, beyond the standard model. Grand unified symmetry breaking, axion physics, or hidden sectors could add new vacuum structure, and each would leave the universe with a different sequence of reorganizations. The idea is not that we know these happened, but that the framework easily allows them. The vacuum landscape is roomy, and nature has not told us how many ridges it contains. Each transition is a candidate for a trigger, because a trigger can be internal. A metastable configuration can persist, then abruptly convert when conditions allow, and the conversion can release energy into new particles. The universe, in this picture, is a chain of state changes rather than a single creation event. The beginning becomes less like a spark from outside and more like a delayed release from inside. To understand that abruptness, we need the concept of a false vacuum. A false vacuum is a local minimum of a potential, not the lowest one, like a valley separated from a deeper valley by a ridge. Classically, a ball in that valley cannot escape without being pushed up and over. The word false is not moral. It is topographical, describing a trap that looks stable until you see the deeper basin. A system can sit in a false vacuum for a long time because a barrier blocks classical motion. Quantum mechanics allows tunneling through the barrier, even without external disturbance, because the wave functional has support on configurations beyond the ridge. The decay is rare, but it is allowed. The vacuum can be quiet for eons, then change without a visible precursor. Historically, this idea was sharpened in the 1970s, when Sidney Coleman analyzed vacuum decay in quantum field theory. The key insight was that the decay rate is dominated by a special solution in imaginary time, an instanton or bounce, which encodes the most probable path through the barrier. The mathematics looks abstract, but it yields concrete predictions. It turned an intuitive picture into a calculable rate, and that shift mattered. In field theory, tunneling is not a particle slipping through a wall. It is a whole region of space transitioning to a new field configuration, because the field value is defined everywhere and must change coherently over a domain. The vacuum is global, so the decay is spatially extended. What nucleates is not an object inside space, but a new phase of space-filling fields. The transition proceeds by bubble nucleation. A bubble of true vacuum appears, and its wall carries the energy cost of the field gradient, like surface tension in a fluid. The bubble is not empty. It is a different vacuum state, with different field values inside. If we could see it, the boundary would look like a thin, luminous shell where the field changes fastest. If the true vacuum has lower energy density, the bubble can expand. The pressure difference drives the wall outward, converting false vacuum into true vacuum, and the wall accelerates toward an ultra-relativistic speed. The expansion is not driven by air pressure, but by the energy difference between vacua. The wall's motion is the field's attempt to replace one configuration with another, as efficiently as causality allows. Inside the bubble, the laws can look different, because particle masses and couplings depend on vacuum values. A vacuum transition is a rewrite of the low-energy world, potentially altering whether atoms can exist at all. It is a reminder that laws of physics often mean laws given this vacuum. We tend to treat constants as eternal, yet the theory treats them as consequences of a chosen ground state. In cosmology, the geometry responds immediately, because vacuum energy gravitates. A change in vacuum energy changes the expansion rate and can reshape causal structure, changing which regions can communicate. Even the horizon structure can differ because horizons depend on how fast space expands. The bubble is not merely a change in contents, it is a change in how space-time itself evolves. This makes false vacuum decay a plausible ignition mechanism for a hot beginning. A high-energy false vacuum can inflate, then decay, then dump energy into particles, producing a hot plasma that resembles the initial conditions of the hot Big Bang. The beginning becomes a transition from vacuum energy to radiation. The bang is not a collision, but a conversion, like stored tension releasing into heat. The energy dump is often described as reheating, but it is also particle creation in a precise sense. As the inflaton or other fields oscillate around a new minimum, they can decay into standard particles, populating the universe with quanta. What looks like matter appearing is a conversion permitted by couplings. The field's coherent motion becomes a spray of excitations, and the vacuum becomes a factory. It also makes false vacuum decay a plausible ending mechanism. If our vacuum is false, a bubble of lower energy vacuum could appear and expand at near light speed, sweeping through space like a silent front. The catastrophe is not fire, but a change in what stability even means. The sky would look normal until the moment it no longer mattered. There is no warning that can outrun the bubble wall. The first sign would be the end, because the causal structure forbids advance notice, and no signal can travel faster than the boundary. The terror is not pain, but sudden irrelevance. Our chemistry would fail because the vacuum changed. Even the concept of after becomes unclear if the new vacuum does not permit familiar structures. This is the chapter's tension, because the trigger that could start a universe can also erase one. The same mathematics that offers an origin also threatens a finale, and it forces us to treat nothing as a loaded term. The vacuum is not neutral, it can be precarious. A calm cosmos may be a temporary truce between competing minima. Now we fold in what we actually know about our vacuum. The Higgs potential, extrapolated to very high energies, may not remain stable, and that possibility is tied to real measurements. The Large Hadron Collider did not just find a particle, it pinned down a parameter in the vacuum's landscape. In the data, a resonance becomes a clue about the shape of a potential we cannot directly see. The stability depends on the Higgs mass, the top quark mass, and the strong coupling constant. Those numbers control how the Higgs self-coupling runs with energy, because quantum corrections from heavy particles feed into the effective potential. In particular, the top quark's large Yukawa coupling pulls the Higgs self-coupling downward at high scales. The top quark is heavy enough that it leaves a noticeable fingerprint on the vacuum's distant terrain. Renormalization group flow is the bookkeeping of how couplings change with scale. It is not optional, because quantum fluctuations at different energies contribute differently, and the theory must absorb those contributions into scale-dependent parameters. The flow is the price of having fields at all wavelengths. It is also a reminder that constants are often summaries of deeper scale-dependent behavior. With current central values, the Higgs self-coupling may turn slightly negative at high scales. That would imply our electro-weak vacuum is metastable, not absolutely stable, meaning it is a local minimum that is not the global one. The picture is subtle. Metastability can coexist with an enormous lifetime. A shallow negativity at high scale can still be separated by a wide barrier, and width matters as much as depth. Metastable does not mean doomed on human timescales. The calculated lifetime can be vastly longer than the age of the universe, given standard assumptions, because the tunneling rate is exponentially suppressed by the action of the bounce. Exponential suppression is nature's way of making allowed effectively never, at least for a long while. The vacuum can be precarious in principle while remaining safe in practice. But the conclusion is not final, because uncertainties matter. The top quark mass is hard to define precisely in the needed scheme, and new physics could alter the running, changing the sign and shape of the potential. We are inferring behavior at energies far beyond any collider, and inference has error bars. A small shift in inputs can move the vacuum from stable to metastable, and back again. High energy thresholds could stabilize the potential, or destabilize it further. We are extrapolating across many orders of magnitude without direct experimental control, and that is a dangerous habit even when the equations are trusted. The vacuum's fate might hinge on physics we have not yet seen. The unknown is not decorative. It sits exactly where the potential's shape becomes decisive. So the Higgs metastability discussion is a clue, not a verdict. It tells us that vacuum stability is an empirical question. tied to measurable parameters, and not merely a metaphysical preference for permanence. The vacuum is a physical system, and physical systems can be tested. Even nothing can be constrained by particle masses and cross-sections. It also tells us that the vacuum is not a passive backdrop. The vacuum is a state with a potential landscape, and landscapes can have cliffs, ridges, and hidden valleys. When we say empty space, we may be standing on a plateau we did not know existed. The emptiness between galaxies becomes a place where the universe's deepest contingency may be stored. If vacuum decay is possible, what sets the decay rate? It depends on the barrier shape, the energy difference, and gravitational effects on the tunneling solution, because space-time itself participates in the process. The rate is not a single number pulled from thin air, but a functional of the potential and the geometry. Even small curvature effects can matter, because the bounce is a global solution, not a local guess. Gravity can suppress or enhance decay, depending on the details. Coleman and DeLucia showed that space-time curvature modifies bubble nucleation in essential ways, changing the bounce solution and sometimes preventing decay entirely. In curved space-time, tunneling includes the cost of deforming geometry. A bubble is born not only in a field, but in a space-time that must accommodate it. A high vacuum energy changes the background geometry, which changes the instanton that controls tunneling. The trigger is not separate from space-time, it is space-time coupled, and that coupling can decide whether a bubble forms at all. The vacuum is not just in space-time, it helps define space-time's evolution. The origin question becomes inseparable from the geometry that makes origin a meaningful term. This returns us to the central question with sharper tools. If the Big Bang was a transition, the cause might be a vacuum instability, not an external agent, and the trigger might be probabilistic rather than mechanical. The beginning could be a decay event written into the state itself. A universe could start the way a metastable nucleus decays, without a prior shove, yet not without a reason. Yet a deeper puzzle appears immediately, because vacuum energy is also what we measure today as dark energy. The universe's expansion is accelerating as supernovae and large surveys reveal, and that acceleration is consistent with a vacuum-like component. The vacuum seems to be speaking twice, at opposite ends of cosmic history. The same concept that may have powered a furious early sprint now seems to whisper in the present. The simplest fit is a cosmological constant, a constant vacuum energy density. Observationally, W is close to -1 within current error bars, and the data so far do not demand a time-varying component. The vacuum, at least observationally, behaves like a steady background pressure. The graphs are almost boring, and that boredom is part of the mystery. But the value is tiny in particle physics units. It is not zero, and it is not naturally large. And that mismatch is the cosmological constant problem, a problem of scale and of expectation. The vacuum energy we infer is about the energy density of a few protons per cubic meter, astonishingly small by quantum standards. In a universe built from quantum fields, why is the vacuum so light? Naive quantum field theory estimates some zero-point energies of modes up to a cutoff. The result overshoots the observed dark energy by an absurd factor, because each mode contributes a half quantum of energy, and there are infinitely many modes. The divergence is not a minor nuisance when gravity makes the absolute value matter. The same bookkeeping that works for particle scattering becomes explosive when the vacuum must gravitate. Depending on the cutoff, the mismatch can be 60 to 120 orders of magnitude. The exact number varies, but the scandal remains, because any reasonable high-energy scale produces a vacuum energy far larger than what the cosmos displays. It is a gap so wide that it feels like a category error. The universe appears to cancel something with extraordinary precision, and we do not know the principle that enforces it. This is not a minor parameter tension. It is a sign that our vacuum bookkeeping is incomplete, or that we are counting the wrong thing, or that a cancellation occurs for a reason we do not yet understand. The vacuum seems to know a rule that our calculations do not. The darkness between galaxies behaves as if it has been carefully tuned. But by what mechanism? In quantum field theory, vacuum energy can be shifted by a constant without changing non-gravitational physics. In general relativity, that constant gravitates, so the shift becomes physical, and the freedom becomes a problem. What was once an arbitrary zero point becomes a cosmic source term. The vacuum is where our two theories disagree about what can be ignored. So the vacuum is where quantum theory and gravity collide most bluntly. The vacuum is not just empty space. It is the interface of our two best frameworks. And the interface is cracked. Every attempt to smooth it reveals how much we rely on assumptions we cannot yet justify. The simplest sounding quantity, energy of nothing, becomes the hardest number to compute. Some approaches invoke symmetry, like supersymmetry, to cancel contributions. But supersymmetry must be broken, and the observed value remains unexplained, because broken symmetry reintroduces a non-zero vacuum energy. The cancellation, if it exists, is incomplete or hidden. The symmetry would have to be arranged so that its breaking leaves almost nothing behind. Some approaches invoke dynamical adjustment, where a field relaxes the vacuum energy. But such mechanisms must avoid fine-tuning and must fit cosmological data, including the near-constant W we observe today. A field that adjusts too quickly ruins structure formation, while one that adjusts too slowly does not solve the problem. The vacuum must be both flexible enough to change and rigid enough to look constant. Some approaches invoke anthropic selection in a multiverse, where many vacuum energies exist and observers appear only in rare ranges. That move connects back to eternal inflation and its measure problem, because one must define how to count vacua and histories. The idea is provocative, but it shifts the burden onto probability and selection. It asks whether the smallness is explained by necessity or merely by survivorship. The cosmological constant problem, therefore, echoes the earlier ignition problem. If vacuum energy powered inflation, why did it have the needed value and then nearly vanish, leaving only a tiny residue today? The vacuum seems capable of being huge and small, but we do not know the rule that sets the dial. A theory of beginnings must explain not only how vacuum energy acts, but how it is chosen. Inflation requires a large, effective vacuum energy for a short time. Dark energy suggests a small, effective vacuum energy for a long time, and those requirements sit uneasily together. The universe appears to have used vacuum energy as a temporary engine and as a persistent background. It is as if the same fuel burned in two different regimes, with no clear explanation for the switch. The vacuum seems to change its role across cosmic history, and we do not know why. The same concept appears in two regimes, yet our theory cannot unify the accounting, and that failure is not aesthetic. It means we do not fully understand what nothing weighs. The emptiest thing in the universe has a mass energy budget, and that budget is the unsolved ledger. This is why nothing is not empty. The vacuum is structured, energetic, and still poorly understood at the deepest level, and that ignorance is not optional if we care about origins. If the vacuum can trigger transitions, then vacuum physics is origin physics. The beginning question becomes a question about state selection and stability, not merely about initial matter. Now we confront causality and triggers directly. In classical intuition, every event needs a prior event and causes precede effects, forming a chain that stretches backward. That intuition is powerful because it matches daily experience, but it is not a law of nature. Physics has repeatedly humbled common sense, especially when probability enters the rules. In quantum mechanics, some events are fundamentally probabilistic. A nucleus decays without a specific external trigger, even though the statistics are predictable, and no hidden clock is required by the formalism. The cause is the unstable state, not a tap from outside. We can compute a half-life, but we cannot point to a particular moment and say what made it happen. Vacuum decay is similar in structure, though far more dramatic in consequence. The decay is spontaneous within the theory, governed by a rate, not by a push, and the rate can be computed from the potential and the bounce action. The event is not scheduled, but it is not forbidden. The trigger is built into the state, like a loaded die, whose bias is the potential barrier. That does not mean the event is uncaused in a sloppy sense. It means the cause is the state and the laws, not a preceding localized disturbance, and the explanation is statistical rather than narrative. We trade a story of impacts for a story of probabilities. The universe can change because the rules assign a non-zero amplitude to change. So a quantum trigger can be internal, and it can occur without a prior signal. The universe can change state because the vacuum is metastable, and metastability is a physical property, not a linguistic trick. The trigger is the existence of a lower energy configuration and a non-zero tunneling amplitude. The moment of transition is unpredictable, but the possibility is written into the landscape. But we must be careful about what we mean by nothing in these statements. Empty space, quantum vacuum, and absence of space-time are different concepts, and mixing them produces confusion that feels like paradox. The documentary must keep the categories separate, even while exploring their overlap. Otherwise, a legitimate mystery becomes a word game. Empty space in classical physics is a region with no matter and no radiation. It can still have geometry, still have a metric, and still allow waves to pass through, even if nothing is currently passing. It is emptiness as a property of contents. A classical vacuum is like an empty room that still has walls and dimensions. Quantum vacuum is the lowest energy state of fields, defined on spacetime. It presupposes a stage on which fields live, even if the stage is curved, expanding, or dynamic. In this sense, vacuum is not nothing, but the most featureless something the theory allows. It is a state with correlations that can be probed, even if no particles are present. No classical spacetime is a different category, where even the notion of a field at a point is undefined. In quantum cosmology, nothing can mean no geometry, not a quiet geometry, and that pushes us beyond the comfortable language of fields on a background. If there is no time parameter, the word before loses its footing. The mind reaches for a timeline, then discovers there may be no line to draw. A boundary condition is yet another meaning, where the universe is specified by a rule on histories. In that case, nothing is not a state. It is a constraint, like a selection principle, that filters which spacetime configurations are allowed. The origin becomes a statement about permitted histories rather than a moment in time. The cause becomes a rule that shapes the whole story at once. These meanings are often conflated in popular language, and that confusion creates fake paradoxes. When someone asks how something came from nothing, they may be mixing no matter with no fields, with no spacetime, and those are not interchangeable. Precision does not kill mystery, it locates it. Once the categories are clean, the remaining questions become sharper, not smaller. When we ask what caused the Big Bang, we might be asking different questions. Did a vacuum decay trigger reheating inside an existing spacetime, with time already defined and a transition occurring within it? Or did spacetime itself nucleate as a quantum event, with no prior time to host a cause? The same sentence can hide two entirely different problems. Or did a boundary condition select a history where a hot phase appears, making the cause more like a rule than a shove? In each case, the word cause does different work, and the answer must match the question's meaning. A mismatch here is not just wrong, it is incoherent. The universe does not owe us a single kind of explanation, because our questions are not always single. In one case, it is a dynamical transition in time, and in another, it is a rule that replaces time. The first resembles a decay in a metastable system, while the second resembles a specification of the entire space-time at once. Both can be discussed scientifically, but they live in different logical categories. The narrator can let the visuals shift, from a clock-like timeline to a block universe diagram, without changing the underlying mystery. Still, the vacuum remains the most concrete bridge between these pictures. It is a physical object in our best-tested theories, and it can store energy and instability, and it can couple to gravity in a way that changes cosmic expansion. Even when we reach for quantum cosmology, we keep returning to vacuum structure. The vacuum is where nothing becomes operational, because it is something we can calculate and, indirectly, measure. So we treat the Big Bang's cause as a change of state, not a shove from outside. A vacuum transition can convert geometry and energy into a hot universe, and it can do so without an external hand. The universe can begin in this framing because the vacuum was not the final word. The beginning is not an exception to physics, but a consequence of physics applied to its most minimal state. That framing also makes a prediction about our ignorance. If vacuum energy is central, then the cosmological constant problem is not a side issue. It is the clue, because it measures our failure at the interface of quantum theory and gravity. The vacuum is the crime scene where the mismatch is visible. We have a number from the sky and no satisfying derivation from the equations. The observed dark energy density is a measurement of the vacuum, and it is telling us we do not understand the vacuum. The mismatch is the universe pointing at a missing principle, perhaps a symmetry, perhaps a dynamical mechanism, perhaps a new way to define energy in quantum gravity. Whatever the solution, it must explain why nothing weighs so little. Until it does, our origin stories carry an asterisk. Now we tighten the tension one last time. If our vacuum is metastable, then the universe's long future is not guaranteed by emptiness, because emptiness itself may be temporary. The end could be a phase transition, as abrupt as a beginning and as indifferent to our expectations. The same quiet that makes space feel safe may be the signature of a state waiting, however improbably, to change. A bubble could rewrite particle masses and forces, making chemistry and structure impossible. The stars would not explode, because explosions require the old rules, but the old rules might simply stop applying. The universe would continue, but it might continue in a form where complexity cannot persist. The tragedy would be silent, because silence is what a new vacuum might enforce. Even if the probability is tiny, the conceptual lesson is large. The vacuum is not a blank page, it is a loaded configuration, and the loading is encoded in potentials we are still mapping. When we stare into intergalactic darkness, we may be staring at a state with hidden tension. The emptiest places become the most consequential, because they are where the vacuum is most purely itself. This chapter's climax is therefore a reversal of intuition. Nothing is not the absence of physics, it is the densest place for physics to hide, because the vacuum is where fields, symmetry, and gravity meet. The emptiest regions are not empty of law, and they may not be empty of consequence. The question is not whether nothing can do something, but what it is already doing. We have chased causes into fields and vacua, and we have found triggers that do not need an outside hand. But the hardest barrier remains time itself, because every trigger we described still assumes a temporal framework in which change occurs. If time begins at the Big Bang, what does cause even mean? The word trigger starts to wobble, because triggers presume a before. If time is emergent, then a trigger may be a boundary, not an event, and the language of before may be a habit without a referent. The vacuum has taught us that nothing is structured, but time may be the structure we cannot assume. In the final chapter, we confront that barrier directly, and we ask whether causality survives when there is no before. We have chased triggers through vacuums, yet the hardest barrier is time itself. In general relativity, space-time is dynamical, so before the Big Bang can be like north of the North Pole. The equations do not place events on a fixed stage. They let geometry evolve with energy and pressure. In that picture, the Big Bang is less a moment inside time and more a boundary where our usual clock simply fails. Classical causality assumes earlier events, while quantum theory allows spontaneous transitions described by probabilities, not pushes. Vacuum fluctuations are not nothing in the everyday sense. They are restless quantum fields with uncertainty built in. Some models replace causal chains with boundary conditions that select whole histories at once, as if the universe is constrained by a global rule rather than a first shove. A self-contained universe could be laws plus initial or no boundary conditions, and the word cause becomes a choice of explanatory standard. That debate echoes earlier shifts in physics, when Newton's absolute time gave way to Einstein's relational spacetime. Inflation explains smoothness and seeds, yet still asks why inflation began and whether it becomes eternal. Quantum tunneling or no-boundary proposals trade a prior moment for a rule, while bounces and cycles trade a beginning for stability and entropy control. Eternal inflation and multiverses widen possibilities, but face measures and testability. How do you count outcomes when elsewhere never ends? Next clues must be empirical. CMB polarization, primordial gravitational waves, large-scale structure, and 21-centimeter maps could narrow the doors. We picture faint B-mode swirls, ripples in space-time, and hydrogen's whisper traced across cosmic dawn. We end with humility. Unknown is not unknowable, and the Big Bang remains robust, even as nothing keeps changing meaning. From mystery to meaning, an answer may be probabilistic, boundary-based, or deeper than causality. We followed the evidence to the edge of the story, where the Big Bang stops being an explosion and becomes a description of space-time itself. Galaxy redshifts, the microwave afterglow, and primordial elements let us rewind with discipline, yet they also reveal a hard boundary where our tested laws thin out. Inflation, bounces, and quantum beginnings try to cross that boundary, but each trades one mystery for another, and each must answer to data. Along the way, nothing refused to stay simple, because empty space in physics is a structured vacuum, alive with fields, pressures, and possible phase changes. Dark matter and dark energy, demanded by the cosmic patterns we measure, still hide their identities, and they may be pieces of the origin story we cannot yet read. Even the Hubble tension, two precise measurements disagreeing about the universe's expansion, whispers that our model may be incomplete in ways that matter most near the beginning. So the singularity is not a final word, it is a signpost, marking where general relativity by itself is no longer enough. And yet, the closer we push toward the first instance, the more the question changes shape, because time is not a backdrop in modern cosmology. If time is part of what emerges, then causality may not behave like a chain of dominoes, and earlier may not be a meaningful coordinate. That is why some answers look less like a trigger in the dark and more like a boundary condition, a selection rule, or a quantum transition that defines an entire history at once. In the end, our best theories do not erase the mystery. They sharpen it, turning speculation into testable differences. B modes in polarization, primordial gravitational waves, subtle fingerprints in large-scale structure, and the hydrogen signal of 21-centimeter cosmology. What we learned is not only what we know, but how we know it, and where the knowing becomes an honest, not yet. We can name the relic light, map its ripples, and read the chemistry of the first minutes. But we cannot yet point to a single, confirmed mechanism that wrote the prologue. Inflation may have happened, but what ignited it, and what field played the role of the inflaton, remain open questions with deep roots in particle physics. Bounces and cycles may avoid a beginning, but they must confront entropy, stability, and the challenge of leaving unique evidence. Eternal inflation may generate a multiverse, but then prediction itself becomes a problem of measures and meanings, not only equations. Still, the journey leaves a coherent picture, even if it is unfinished, because the universe is not silent about its past. The patterns in the afterglow tell us the early cosmos was hot, dense, and exquisitely uniform, yet seeded with tiny imperfections that became every galaxy. Those imperfections are the closest thing we have to an origin signature, and they may carry clues from physics beyond our current reach. The Big Bang, then, is both a triumph of explanation and a horizon line, where the map ends and the next survey begins. We began with a question mark in the dark, and we end with a different kind of darkness, one that is not empty but richly defined. The vacuum is not nothing in the philosophical sense, and even no space-time may be a category our current language cannot cleanly describe. When we say cause, we usually mean an event inside time, but the beginning may be the place where time itself is one of the things being explained. That is not an escape hatch. It is a reminder that the deepest questions often demand new definitions before they can accept an answer. So the story does not collapse into ignorance. It resolves into a boundary we can approach from multiple sides. On one side are observations, getting sharper year by year, forcing our models to earn every claim. On the other side are theories of quantum space-time, vacuum dynamics, and cosmic beginnings, each trying to turn the singularity from a wall into a doorway. Between them is the method that made cosmology possible, the refusal to confuse a convenient metaphor with a measured fact. And perhaps that is the most important revelation, because the Big Bang is not a single statement, it is a scaffold of evidence. It tells us how the universe evolved from an early hot state, but it also tells us exactly where that explanation stops.